Someone is not muting themselves. Okay, yeah, and yeah, Michael, you can bring up your slides. Yeah,
you can hear me, right? You can hear me and you can see me. I start sharing my screen.
You can bring up yourself. Just give us a minute to get started. But yeah, bring up your slide.
Can you see it? I put it in full screen.
Yes, yes, looks good. Thank you.
Yeah. Can I start?
Hold on, just hold on a minute.
Yeah.
Yeah, we'll let, so Robert Favell is the chair and we'll let him introduce you. And I don't know if he wants to say a few things first.
Okay, are we ready?
Yes, we are ready.
All right. Good morning, or whatever time of day it is for you. I'm Rob Favell from SUNY Albany, chairing this session. We have 5 talks. The first talk will be given by Madhu Latha, who will talk about the structure of latent heating rate in the severe convective environment using Wharf simulations. Take it away.
Yeah, thank you. Hello, good morning, everyone. This is Madhulata Akiseti from IMD, India. Today I'm going to present my previous work conducted at Korea Institute of Atmospheric Prediction System, KIAPS, South Korea, in collaboration with NCAR. I would like to thank all my co-authors, particularly Dudya sir, for fruitful discussions, and all the other co-authors for their encouragement and support. I also would like to acknowledge Dr. Song-Yu Hong, then Director of KIAPS, for his encouragement and initiating the collaboration with NCAR. And also I would like to thank the other colleagues of KIAPS for their necessary inputs. And today I'm going to discuss about the structure of latent heating rate in severe convective environment. And before going to that, why we need to study this latent heat, what is the importance, means the water vapor in the atmosphere, when it convert into the cloud, when it forms as a cloud, you can see the water vapor which convert into different forms. If you see the cumulus or cumulonimbus cloud, it consists of both solid and liquid hydrometeors. During the transformation of vapor to liquid and solid form in the cloud, it releases a lot of latent heat, means it will release and heat, and it causes latent heating. It releases and absorbs the heating, and it affects the storm dynamics in the small scale, and also in the large scale. Latent heating is very much important to explain the transfer of energy in terms of mass, momentum, and moisture in the atmosphere. Basically, in the numerical models, these different hydrometeors are modeled using microphysics schemes. If you see this panel, there are 2 types of processes, before and above freezing level. As I already told, below the freezing level, it is mostly the liquid hydrometeors. The complexity is little low. Above the freezing level, there is a mixture of both solid and liquid hydrometeors, and due to the differences in habits of different ice and gravel particles, a lot of complex processes are involved. I'm not going into the detail, but you can see the picture. They are so complex. These are modeled using different microphysical processes. So in this study, we tried to simulate the latent heating rate using these microphysical processes, basically using WDM6 scheme. Coming to the system description, we have considered a severe convective system happened over South Korea in 15 to 17 July. It has caused record-breaking rainfall over Cheongju region. Different platforms from TRMM, weather radar, and satellite showed the severe convective system. And from the KMA synoptic charts, it is evident that this system has formed associated with the frontal forcing in the Changma season. reason. Due to the stationary front, it has created a lot of rainfall over this region. You can see the rainfall associated with the passage of the front, and coming to the we have conducted the numerical simulation using 4 nested domain. You can see the domain here, 27931, and for model domain, we considered WRF with version 3.9.1, and the NSEP FNL data is considered for initial analysis. For PBL and Cumulus, we have relied on the scale aware scheme, which are not at all, which are different from the traditional Cumulus schemes, which are not at all run at the high resolution. But these will in the innermost domain also, these are on scale aware schemes. And basically here the microphysics schemes we considered is WDM6 scheme in all the domains. And coming to the computation of latent heating rate is based on the Lee et al. It is the function of the microphysical transformation processes and the latent heat constant and the specific heat capacity. You can see the formulas here. We considered the basic 6 microphysical transformation processes: condensation, evaporation, freezing, melting, and sublimation and deposition, which cause latent heat release and absorption when the parcel transform from one phase to the other. These I just mentioned in detail what are the processes are going on in the computation of these latent heating terms in separate. And I'm just giving the different production rate terms included in the WDM6 module for calculation of these cloud hydrometers along with the number concentration. Basically here these production rates are outputted into the WRF output. You can see this one, and basically the warming and cooling associated with these different latent heat terms will be discussed by completing this simulation. And before going to the latent heat, I just showing the innermost domain. You can see the in the innermost domain, if you see the WRF over the Cheongju region, TRMM and AWS both shows heavy rainfall was happened over this region associated with the MCS. There are temporal and spatial differences between simulation and observation. It will be obvious. So in order to simulate the rainfall latent heating, we have considered a precipitation core, this black box, rectangle box over the Cheongju region, means this region where the model has simulated better. And based on TRMM and WRF observation, the developing and dissipating stages of the systems are classified. When the rain was initiated over the model, the developing stage was considered, and the decrease in rainfall, according to the decrease in rainfall, the dissipating stage is considered. It should be noted that in the model the model simulates early initiation compared to the TRMM. So now I am going to discuss about the simulation of latent heating over these convective regions in the next slides. And before going to explain about the latent heating associated with different phase change processes, here I am just showing the production rates rain condensation and condensation activation, and rain evaporation is from precipitation, rain, grapple, and snow evaporation. Using all these terms and based on the specific heat constant and other things, we calculated. You can see this one is the condensation, a latent heating rate associated with the condensation. You can see the positive, and associated with the rain evaporation, it is negative. These are basically condensation and evaporation, and a similar way, the freezing and melting. You can see these are the functions of homogeneous freezing, heterogeneous freezing, and grapple. And also the process involved are accretion and the auto conversion for freezing and melting. You can see the freezing process is positive, and the melting latent heat associated with melting is negative. Similar way I am showing for the deposition also. These are basically based on ice and snow, grapple, deposition, and ice generation. These different latent heats explains the transformation of water vapor into different phases, liquid and solid. So now I am going to show the vertical distribution, average, dissipating, and developing stages, I already showed the classification based on the rainfall. If you see in the developing stage, the latent heat of condensation is dominated at 600 hectopascal, and above this latent heat of deposition is dominated. It explains the transformation of water vapor to liquid at the lower levels, the latent heat release, and at the upper levels it is due to the transformation from liquid to solid hydrometeors. Basically the positive latent heat release is evident, and also you can see in the developing stage there is evaporation, and also there is contribution from evaporation and melting, because when the system has passed towards this region, it is already in the mature stage, so you can expect both updrafts and downdrafts. Means it is already raining, even the cloud is forming and the rain is also happening. That's why negative of processes, cooling process are also evident. If you see the cloud hydrometeor distribution, you can see the lower levels associated with the evaporation, the cooling associated with the rain, and the Q cloud associated with the ascent of parcel, which is attributed to the condensation release, this one. And at the upper levels, it is just explaining the conversion of water vapor into different hydrometeors. At lower levels, liquid hydrometeors, and upper level solid hydrometeors, and the corresponding latent heat release and absorption. And if you can see the updraft motion is dominant, and in the lower levels there is downward motion. Since already rain is happening, it is in mature stage, and we try to see the impact, means contribution of different microphysical processes. If you see basically the condensation activation are followed by deposition are contributed for major heating, and the cooling is from the rain and cloud evaporation followed by melting. These processes are contributed for warming and cooling in the developing stage of the system. So if I go to the next slide. Yeah, in the dissipating stage, if you see the same way, if you see the cooling is dominated because it's already in the dissipating stage. Major contribution is from condensation is major contribution of latent heating is negative is from rain evaporation, and also there is a positive from deposition is there, because at the upper level still stratiform portion of cloud is there, and cloud is ascent is going on associated with this latent heat of deposition positive is evident. And if you see the cloud hydrometeor structure here, the cloud ice and cloud snow, basically the solid hydrometeors are dominant because it's already rain is happening and associated with the stratiform portion of the rain. And if you see the average vertical velocity downdraft motion is evident. So when you see the contribution of microphysical processes, the dominant warming is attributed to the ice deposition. You can see this ice deposition means warming by the ice deposition, and cooling is from the rain and cloud evaporation. So if we see the evaluation of different parameters in the storm environment, if you see the total hydrometeors, it represents the conversion of water vapor into cloud and distribution to different solid and liquid hydrometeors. This is the total hydrometeors from the model. In the convective developing stage, you can see the high vertical cloud, and in the stratiform dissipating stage, you can see mostly the solid hydrometeors correspond to ice and grapple are evident. Accordingly, positive latent heating, this is the total latent heating from all the transform. Positive heating is dominant, explain the latent heat release associated with the ascent of air parcel to the upper level. And in the later portions, you can see the negative latent heat absorption due to the descent, means solid to vapor. This is and if you see the updraft velocity in the
12 minutes.
to develop, yes, I will. In the developing stage, it is more positive and it is negative. And in the rainfall also, you can see more is in the developing stage. Since it's the system, the rain got evaporated in the dissipating stage, not much rain is evident. So you can see that the ascent of air parcel from surface to upper levels and latent heat release associated with the transformation of air parcel is clearly evident, and consistency between the different parameters is clearly evident. So Therefore, the choice of microphysics plays important role in simulation of severe convective system, as they all are interrelated and it affects the storm dynamics. And coming to the inference, we try to compare this latent heating rate simulated from the model by calculating the Q1 and Q2 terms based on NI et al. 1973. Basically, the Q1 is the total diabatic heating, including the net radiative forcing and latent heating, and also the turbulent mixing. But if you see, take the moisture sink, it is attributed to the latent heat release due to condensation and evaporation. If you see the second and third panel, the model is reasonably able to capture the latent heating associated with this severe convective system. So quantifying these so if by quantifying these latent heating simulation, the uncertainties in microphysical processes and the assumptions can be, the biases can be understood, and it may be useful for further improvement. And also simulating these latent heating profiles can help to test the sensitivity. Now here I am showing double moment scheme, and you can see the single moment scheme and which process is acting better and which process has contributed in the vertical distribution of the cloud, and it can act very helpful proxy to test the sensitivity of different schemes and also further improvement of the scheme. And also one more thing is by comparing with the Q1 and Q2, we can differentiate specific heat process in the atmosphere, and also this can be useful to develop parameterization of organized convection. So by simulating this latent heating and by understanding and assessing the bias, it can be useful to further improve the microphysics as well as cumulus physics schemes. So currently this paper is under review, and thank you all, and I would like to thank organizers for giving this opportunity to present this work. I'm open for questions.
Okay, we have time perhaps for one quick question. So I'm wondering about, you compared your Wharf precipitation to the trim, and I noticed that the trim precipitation occupied a much larger area of rainfall. Is that an issue with the observations, the low resolution of the observations, or does the microphysics scheme not produce enough stratiform rain?
If you see with AWS, you can see the high resolution observation. I am showing, can you see my screen?
Yes.
Yeah, if you see the AWS, you can see this is also similar to model, means this is high resolution, but anyway, model is not able to capture the spatial band over this region.
Okay. All right. Thank you for your talk. Our next speaker is Yu Chin, who will talk about simulating the morning transition of flow over the eastern Snake River plain.
Hi, can you hear me okay and see the screen okay?
Yes.
Thank you. Yeah, hi everyone. My name is Yu Chin and I'm a PhD student at Boston University. Today, I'm very happy to be here to share with you some preliminary work on simulating the morning transition of flow over the eastern Snake River plain. As we can see from the animation down below, on the left, I'm showing the observed wind field by my local observation system. And on the right, I'm showing the simulated temperature field. And they are going through a processes called the morning transition. And as I will discuss later, the temperature field and the wind field are closely correlated. So since the introduction of the Abukov lens, micrometeorologists were specifically interested in the perfect site that has a flat, uniform, and horizontally homogeneous surface. Under such conditions, the constant flux assumption can be satisfied with sufficient accuracy within the surface layer. The logarithmic law of the mean wind velocity and the Munio-Bukov similarity theory will be applicable. Therefore, most numerical models in the surface layer depend on experiments conducted over flat terrain to parameterize turbulent exchanges between the surface and the lower atmosphere. And decades after, the nuclear power meteorological community required knowledge on how hazardous materials would disperse if they are released into the remote sites, which are frequently in complex terrain. Therefore, it inspired a lot of research on the complex and spatially inhomogeneous terrain with irregular topography or variation in land use, such as mountains. These terrain are therefore imperfect sites from the Munio-Bukov similarity theory point of view. However, the real terrains often lie in between the perfect and the imperfect site. They are usually characterized by a mild slope or surrounded by complex terrain, but it can still generate local circulations that complicate the land atmospheric interaction processes and also result in deviation from the Munio-Bukov similarity theory-based parameterizations. A key feature of the climatology over complex terrain is the diurnal cycle of the slope wind system, which is driven by the buoyancy force. During the night, the air close to the surface is cooler than the air far away from the surface at the same altitude. Therefore, buoyancy force will push the air parcel downward. And during the daytime, it's the opposite case, where buoyancy force pushes the air parcel upward due to radiative heating effect. In between the previous night and the next morning, the flow undergoes a reversal of wind direction, and that is the morning transition period. So why does the diurnal slope wind system matter? Because a better understanding of the slope flow system is of essential importance in many areas. For example, it can help us understand the distribution of air temperature, and also the transport and dispersion of air pollutants, and the local weather forecasting, such as wildfires, snowstorm, etc. And also the operation and construction of wind farms, and the agriculture, such as frost hazard and irrigation, also the formation of low clouds and fogs. While the driving mechanisms of the morning transition of the slope winds have been well understood, it still remains a lot of challenges in numerical simulation of the slope winds. For example, the nocturnal boundary layer is hard to parameterize. And the parameterization of the morning transition phase is less well established than the fully stable and fully convective states. Also, we need to prevent the runaway cooling in the model by manually enhance the turbulent diffusivity, which can cause some side effects. And also some assumptions such as stationarity, non-subsidence, no radiative flux gradient can be violated during the morning transition in the complex terrain. And high resolution land surface data are required. Therefore, we are inspired to explore the performance of numerical weather model in simulating the morning transition of flow over the terrain with a mild slope. Specifically, we would like to address the following questions. How well can numerical model capture the local flow and temperature features under the influence of slope winds? What are the key factors that affect the simulation of the slope winds? Next up, I would like to introduce my study site. The Eastern Snake River Plain extends from Twin Fall, Idaho, to the Yellowstone Plateau on the northeast. The general orientation of the Eastern Snake River Plain is northeast-southwest, bordered by large mountain ranges. Immediately to the northwest are the Lost River, Lamhigh, and Bitterroot mountain ranges. These mountains are perpendicularly orientated in a northwest-southeast direction and rise to approximately 300 meters above the mean sea level. Across the Eastern Snake River Plain, the elevation is higher to the north and northeast and lower to the south and the southwest. Along the 50-degree azimuth angle, the overall difference in elevation is 350 meters, and the distance between the highest and lowest point is around 200 kilometers, which gives us a relief ratio less than 0.002. This mild slope and the orientation of the area play an important role in the specific climatology in this area. Can someone mute themselves? Okay, thank you. During the nighttime, when the thermally driven wind plays an important role. The dominant flow is the drainage flow from the northeast down to the southwest, because there's a mild slope along this axis. During the day, the prevailing wind direction is from the southwest. That's because the study area lies in the mid-latitude, which is called the westerlies, with the prevailing synoptic wind from the west to the east direction. And the bordering effect of the mountains will channel the surface wind along the southwest-northeast axis. Then I would introduce the local observing network. The Idaho National Laboratory has 34 fully automated meteorological observation stations in operation, which are now called the INL Mesonet system, and they continuously collect meteorological data for a long period of time. We also have a edicovariance tower, GREE, located in the southwestern part. It is easily influenced by the general down valley wind from the northeast that developed during the night, and by the shallow surface flow that moved down the Big Lost River channel from the northwest. Starting from September 2020, GREE has turbulent measurement at 12 levels, and also it has radiation and fluxus measurement. Now let's move on to the Wharf configuration. In the innermost domain, the horizontal resolution is 1 kilometer by 1 kilometer, and the lowest vertical level is 10 meters. For the baseline simulation, which is conducted on October the 4th, 2020, we use 7 hours spin up, and the forcing is NAR. The radiation scheme is RRTM. We use ACM2 PBL scheme, and accordingly, we use plane suit, LSM, and surface layer scheme to match with the ACM2 PBL scheme. And for sensitivity tests, we test the different PBL schemes, different land surface model, surface layer schemes, and such, etc. We also highlight that in order to represent the surface features, we use high resolution land surface data set as listed here. All sensitivity tests show a good agreement between simulation and observation in terms of the radiation component and surface fluxes. Therefore, I will only focus on the wind and air temperature here. Also, because all sensitivity tests show very similar results in temperature and wind, I will only present the baseline simulation. So here I'm showing the evaluation of the wind field. Before sunrise, the area is under nocturnal stably stratified conditions with a temperature inversion. Turbulent transport between the surface and the free atmosphere is very weak. Therefore, the synoptic westerly wind is constrained. Instead, the surface layer is dominated by the topography-induced downslope wind from the northeast, down valley wind, and the downslope wind from the northwest. The top row is showing the Wharf baseline simulation, and the bottom row is showing the observation by the Mesonet system. We can see that at 340, the model clearly underestimated the drainage flow in the in this southwestern part of the INL compared to the observation. At 5 8:50 a.m., the model develops a down valley wind at Gree at our flux tower and downslope flow in the northwest INL, but it's weaker than the observed. At 8:30, most stations in southwest INL are dominated by downslope wind from the northeast, while the model underestimates the wind speed. So in general, it's found that the numerical simulation underestimates drainage flow at night. Then after sunrise, the temperature inversion is gradually destroyed by radiative heating. So we will see the transition between downslope wind to upslope wind. At 10:30 a.m., the wind is very weak in simulation, indicating an onset of the wind reversal. Stations at southwest and southeast INL are already showing upward flow. And the Greek flux tower site is under the competing effect of both downslope wind and upslope wind. So the flow seems to cease and experience a lot of intermittencies. Then at 11 a.m., the simulation shows a southwesterly upslope wind in most places, while in the observation, Gree is undergoing east wind, which could be due to the combined effect of the downslope wind from the northeast and the up valley wind from the southeast. Finally, at 12:30, while the model is showing prevailing effect of southwesterly wind, in observation, most places are having south wind, thus an underdeveloped upslope wind. And therefore, in general, the Wharf model predicts an earlier wind shift from the northwesterly downslope wind to the southwest upslope wind. Here I'm showing the evaluation of the 2-meter temperature, and the orange line showing the baseline simulation and black dot showing the observation. We found the air temperature increases with height, and the hot bias accumulates throughout the night. And especially at the lowest level, which is the 2-meter air temperature, we found the largest hot bias, which is up to 9 Kelvin. And also, gradually, the hot bias collapses when it goes upward. This is showing other sensitivity tests, which shows no PBL scheme is clearly superior than others. So we found a connection between temperature and wind biases. First of all, because we have lack of drainage flow, we have less cool air drainage effect at the low-lying areas. Therefore, it will underestimate the model. The model underestimates the drainage flow will cause insufficient cold air drainage at the southwest INL, and therefore it will have less temperature decrease than the observation at night, namely less hot bias. On the other hand, because the near surface temperature in the model is hotter, it will generate less downslope wind, and therefore it will cause earlier morning transition. And here's some assumption of the causes of hot bias. I want to highlight that I hypothesize there are too much turbulent mixing from above the surface layer, because it mixed too much hotter air from above to the ground by the manually enhanced eddy diffusivity of heat. So, but I tried to manually reduce the eddy diffusivity of heat, but it didn't seem to work, and it didn't create different results. So I think there's some mechanism in the model that hinder the diffusivity from being too low. And also there's might be some local topography that is not captured in the mesoscale simulation. This is the summary. So first of all, we found among all the PBL scheme and sensitivity tests, Wharf underestimate the drainage flow and significantly overestimate the near surface temperature at night over the study area. And we found the feedback loop between the underestimation of the cold air drainage effect and the hot bias at night. And also we found probably the eddy diffusivity under stable condition could create too much over mixing effects, which need further examination. And that's all for my presentation. And I would love to take any questions and suggestions and remarks. Thank you very much.
All right, thank you. Are there any questions? Dave Stoffer? You're still muted, Dave.
Okay, can you hear me?
Yes.
That was an excellent presentation. That was very, very nice. I just wonder why you didn't use the MYNN EDMF. Use the MYJ and the YSU and the ACM2. The EDMF, I know from my experience that the transition zone is often different between the MYJ and the EDMF, and I would encourage you to try that if you haven't already.
I haven't tried MYNN. It's because I'm more familiar with ACM2, and it's non-local, like turbulent transport parameterization. But yeah, I think I will try that after this presentation.
Yeah, again, nice job.
Oh, go ahead. In the
I just said
chat,
nice job. All done.
Thank you.
all right, thank you. In the chat, Wayne Angevine says he recommends taking a close look at the soil temperature and moisture initialization. The soil boundary condition is extremely important.
Yeah, in sensitivity tests, we did try different initial soil moisturization and also the soil temperature, but it didn't make differences in the hot biases. So I'm still confused about why the hot bias is so huge.
I put a link in the chat to a paper which you may find of interest, and I'm happy to discuss it with you offline.
Thank you so
Okay.
much. Yeah.
All right. So let's move on to our next talk. Thank you. Our next talk will be from Joo-Hae Kim, who will talk about day-ahead forecasting of solar irradiance using Wharf Solar and evaluation using the National Solar Radiation Database.
So hello, can you hear my voice?
Yes, you're not in full screen yet.
Okay.
Presentation mode. There you go.
Okay, yeah. Hello everyone, I'm Joo-Hae. Thank you for your attention to this presentation. Today I'm gonna talk about day-ahead forecasting of solar irradiance using Wharf Solar and the evaluation result using the National Solar Radiation Database. The recent development of Wharf Solar forecasting system will be introduced first, and the experiment design will be followed. And I will show you the forecast evaluation result and a summary. The Wharf Solar forecasting systems focused on the prediction of the global horizontal irradiance, which is downward shortwave flux. The figure on the left shows the observed GHI at a specific time step, and the figure on the right shows the predicted GHI from Wharf Solar deterministic forecast. So you can see clearly that GHI are affected by the distribution of clouds. Over the past few years, we have developed an ensemble forecast system optimized for the solar energy prediction. So Pedro already introduced about the development process of the Wharf Solar EPS in his previous talk, so I will add some details. So Wharf Solar EPS is the stochastic ensemble prediction system based on the deterministic Wharf Solar. So at first, the most relevant variables for the largest uncertainties in predicting surface solar irradiance and clouds have been identified with tangent linear model of selected parameterization. So Yang et al. Details the methodology. Now in this box plot, you can see the GHI is sensitive to surface albedo and aerosol optical depths in clear sky, and highly sensitive to cloud amounts in the cloudy conditions. The table on the right shows the selected variables to perturb. So surface albedo, aerosol optical depths, Armstrong exponent like aerosol properties and the clouds and the other variables. So we perturb those variables inside each of the 5 parameterization. This figure shows the distribution of stochastic perturbation for the aerosol optical depths and the turbulent kinetic energy on the warp solar domain. The perturbation pattern is homogeneous with a horizontal length scale lambda and mean of 0 and a variance of sigma square. The tau is the decorrelation time. Depending on defined stochastic parameters, the quantity of 14 physics variables changes throughout the forecast time. And the below figure compares the time series of predicted GHI from warp solar deterministic and the warp solar EPS with the SAFRAD observation. All ensemble members tend to exhibit GHI forecast similarly in the clear sky region, while the individual members perform differently in cloudy regions. The impact of stochastic perturbation is more pronounced in cloudy region, and this is very positive. And I will introduce about the National Solar Radiation Database. This is a satellite-based solar irradiance observation, and it provides the GHI and Diurnal information at 4 kilometer resolution. This data is known as to show 5% bias in GHI against the surface side observation. And in this study, this data was regraded into 9 kilometer resolution warp solar domain for 2018 for validation of the prediction result. Now, of course, there are advantages and limitations of using a satellite-based observation, but I would like to highlight its strengths here. So when you look at the result, 2 figures compare the mean absolute error of the warp solar GHI forecasting using the NSRDB and the ground observation. It demonstrates the advantage of excellent spatial resolution of NSRDB. And Jimenez 2022 says that the NSRDB tends to provide a slightly better statistic than the those obtained with the high quality ground observation on seasonal or annual timescale. And this is the gold satellite image, which shows the cloud coverage over the corners. And the NSRDB detects the detail of clouds very well. This is an experiment design. So we will compare the forecast results of 4 different prediction systems, which are deterministic warp solar EPS, SCAPS, and the warp solar multi-physics ensemble system, especially focusing on the impact of stochastic perturbation in the warp solar EPS. The 48 forecasts were conducted, initialized at every 6 UTC, which is optimized for the day ahead solar irradiance forecasting. So evaluations are conducted for every 5 by 5 grid point of the warp solar domain using the NSRDB observation. The 3 experiments, warp solar deterministic, EPS, and SCAPS, they have the same physics configuration, which is the reference configuration of the warp solar. And the warp solar multi-physics ensemble has 10 different combinations of physics scheme. So this is the summary of warp solar multi-physics ensemble configuration. So it combines the reference physics scheme with other microphysics, cumulus, shallow cumulus, aerosol, and the radiation schemes. So I will skip this part. Now I will show you the spatial distribution of annual averaged bias of GHI prediction. So let's look at the 2018 GHI distribution from the observation. So you can see the high GHI values in the southwestern United States, and the northeast shows the lower solar irradiance. When you look at the distribution of bias, all of Wharf forecasts are shown on the overall positive bias. And the Wharf deterministic and Wharf EPS and SCAPS, they show similar pattern of bias with the largest positive bias in the southeastern United States. But the Wharf EPS shows slightly more positive bias than the other two. Compared to these three, the Wharf physics shows a different pattern with the largest bias in the central United States and reduced bias in the southern area. This is probably because different physics options were used in this experiment. This figure shows the mean absolute error. The figure on the top right shows the cloud optical depths from the NSRDB. And the old forecast shows the largest mean absolute error in the eastern United States. The regions with large errors are highly correlated with the optically thick cloudy region. The three ensemble forecast improves the predictability in most regions, especially in the eastern United States. And the Wharf EPS reduces the mean absolute error in Wharf deterministic by 7.5% in GHI predictions. Yes, of course, the SCAPS and the Wharf physics greatly improve the forecast error in the eastern United States. And these are the correlation maps. The correlation coefficient shows the high values in the western United States and lower values in the east. The ensemble forecast shows higher overall correlation than the deterministic forecast in most regions, especially in the eastern United States. I'll show some ensemble evaluation results. So a rank histogram is one way to evaluate the characteristic of ensemble, computing the probability of occurrence of observation in its set of forecast beam in increasing order. So if an ensemble is perfectly statistically consistent, its rank histogram is flat. So in this case, the three ensemble shows the U-shaped histogram revealing the under dispersion in a very similar way. And the Wharf EPS has the highest left bars, which means the small GHI values exist more frequently in the observation, which indicate there should be a positive bias in the forecast. A rank histogram can be presented together with the missing rate error. A large positive missing rate error reveals a more under-dispersive ensemble. Wharf physics has a relatively better dispersion relationship, followed by SCAPS and the Wharf EPS. The figure on the right is the beamed spread scale, which compares the root mean square error of the ensemble mean and the standard deviation of 10 ensemble members. One-to-one diagonal line represents a perfect spread scale agreement. In the result, SCAPS and the Warp solar physics are closer to one-to-one line compared to the Warp solar EPS, but all experiments shows under-dispersive ensemble.
12 minutes.
The frequency of predicted clouds of the 4 experiments were compared with the cloud frequency in the NSRDB. Here is the MPAS scale score. SCAPS and the Warp solar physics shows slightly better performance over the Warp solar EPS in detecting clouds. And figure on the right shows the frequency of with respect to the different amount of cloud optical depths. So model tends to produce optically thin clouds more frequently, and the medium thickness clouds less frequently than observation. And Warp solar EPS produces less optically thick cloud than other prediction. So this is the summary. Day ahead forecast of solar irradiance were conducted by using 4 forecasting system. And using NSRDB as an observation data set enables evaluation of the spatial distribution of the error reduction over the corners. And Warp solar EPS shows a slightly higher positive bias than the others, but mean absolute error decreased by 7.5% compared to the Warp solar deterministic. SCAPS and Warp solar physics shows a slightly better performance over Warp solar EPS in general, but all of the 3 ensemble systems produce under-dispersive, unreliable, and the overconfident ensemble. The results provide some guidelines for improving the performance of Warp solar EPS in the future. Thank you. I will take the questions.
Okay, thank you. Are there any questions? Can I ask you about your histograms? You showed the rank histograms.
Sure.
Yes, so I noticed that Wharf solar EPS that looks like a very symmetric histogram, okay? But the other ones are not, they're more asymmetric. So I kind of wonder if there's a little bit of a clue hiding in there regarding how to address the under-dispersion problem.
Oh, that's a great point. I didn't think about it, but yeah, you said in this medium range area, yeah, this Warp solar EPS looks more, yeah, they look similar, and this one is a little bit different, but yes, I will think about it, but this indicates the smaller GHIs, so it indicates the cloud regions are more frequently observed in the observation. So this one is very good. So the line is matched. So observation and the prediction predicted GHI are same in this number, in this GHI area. So yes.
Okay. All right. Thank you. Wayne Angevine comments in the chat, 10-member ensembles are probably always going to be under-dispersive. There's good literature on the number of members needed.
Okay.
Okay. All right. Thank you. The next presentation will be by Marta Gil Baraji. So I'm probably 0 for 4 in pronouncing these names correctly. Who will talk about Mpass powered downscaling solution for winds.
Hello, everyone. Can you see my screen and hear me correctly?
Yes.
Perfect. So my name is Marta Gil Baraji, and I'm going to present the research that we have carried out in my company at Vortex And I want to thank my colleagues, Gerard Cabero and Pau Caso, and also Pedro Peixoto from the University of Sao Paulo. So basically, this company is involved with generating virtual wind data for wind resource assessment. So what we do is we convert macro scale data, like reanalysis data that explain how the meteorology in the past was behaving, to micro scale data using dynamical downscaling. So we have basically been using Wharf all these years, and what we have done now is to evaluate what's the performance of changing over to Mpass. So what I'm first going to explain is how are the meshes of Mpass designed so as to be of use for the wind industry. And I'm going to explain which is the reference Wharf simulations that we have used in our study. We have done some sensitivity tests on the meshes and then some benchmark validation against real measurements to make sure that the meshes were real. So for a little bit more of context, what we do is we model the wind to obtain wind data and obtain time series of raw wind data that wind engineers can use to assess which kind of turbines or where they want to put the turbines exactly. So what we've doing all these years is we use the boundary conditions, eta 5, for example, as a reanalysis to power a 9-kilometer Wharf domain. And then we do some nesting so as to reach to higher resolutions. One option which is available in Wharf that we use a lot is nudging, because this allows us to influence the outer domain of the simulation and make it follow the reanalysis more closely. So now I'm going to explain about which are the meshes that are of interest for the wind industry. The ones that are available freely in the Mpass page are not really focused on what we would like to have, but because what we want are long-term wind data time series at specific locations or small regions. So what we really need is a variable resolution mesh that has a central high resolution area and then transitions to low resolution to reanalysis resolution. And all the while keeping the smallest possible number of cells that still makes sense, but allows us to run it in a reasonable time. What we have developed is a mesh generation tool that will be open source and in a repository that allows us to go from a map of the world that says a certain resolution at each location to an Mpass mesh with the cells that have that resolution at the required place. For this tool, I have used part of Pedro Peixoto's work that also comes from other repositories that are open source, like Mpass tools and Jigsaw and other meshes available. So what I want to explain now is which is the template of the meshes that we have used and we think are useful for wind industry analysis. And what we have to take in mind is that what we want to model is just one point, the central point of the domain. Okay, so that's where we want to obtain a valid time series, and we really don't care about the rest of the simulation space. What we do is keep a high resolution area. High resolution in this context would be 3 kilometers of a certain size, and then let the resolution increase linearly until a threshold resolution of 20 kilometers that we've set. And this margin can be changed, and it's 100 kilometers in this example. Afterwards, we keep this 20-kilometer resolution constant for a few kilometers so as to allow for some buffer of the region that we're going to cut. And after that, we don't care anymore. So we allow the resolution to increase linearly until a maximum resolution of 1,000 kilometers. After this 1,000 kilometers, we keep the resolution constant so as not to have very huge cells. And this all the while takes 35 seconds. We can do lots of different meshes with this technique too, and this is kind of something that we will explore in the future. But basically now what we want to do is to test if these meshes that we have created actually give sensible results. So we want to compare it with Wharf simulations. Here we have the first problem because it's not straightforward to find an equivalent Wharf given an Mpass simulation. What we have seen is that we want to try two versions of Wharf. One that has this nudging option we were talking about of having the outer domain being a little bit fixed by reanalysis, and the other one without this option, which is not available in Mpass. And all the while, we try to tweak the settings of the models to maintain the same vertical levels, the same static fields, and more or less keep the same physics going. And we also needed to decide how many domains and which sizes we wanted to compare with. So what we do is, given an Mpass mesh, we move it to the point where we want to make the simulation. We cut a region of the given radius, so the part where the resolution stops increasing in that zoom part. And then we created a region using Mpass limited area tool. Once we have this Mpass mesh, we generate the equivalent Wharf domains, what we called equivalent simulation, which is a 9-kilometer domain, which is going to cover more or less the area of the full Mpass region, and then a high resolution 3-kilometer domain that is going to cover the inner circle of the Mpass mesh. Once we have this, we implemented some sensitivity tests. The idea was to test several Mpass meshes and their equivalent Wharf simulations, changing the sizes from very small 15-kilometer radius inner domains to a little bit larger 50-kilometer inner domains, and also changing the margins, like how smoothly did we change the resolution, which is, and we tested this range to see how much computer power we could save and how small could we make the meshes. We tested it at the Perdigal test site and tested for 2 months. And here we have the results of the validation of the central point time series at 100 meters. First, we can look at this map, which is the correlation of the wind. And we have on the one side here, which are the results of the reanalysis, the raw reanalysis without the model. And we see that doing this modeling improves the correlation of the wind in this site. And we see that Mpass is very robust and is not so sensitive to the domain sizes as Wharf with Bozo options, that where the inner domain size, so the smallest domain size, really influences the final result. We see the same behavior with the root mean square error. And another very important detail, of course, is that the Wharf with nudging seems to perform the best in both cases, but followed very closely by Mpass, whereas Wharf is lagging behind. And this is very interesting for us, and something that we want to check if it happens the same for all sites. So that's where the benchmark relation that I'll explain later will come. Right now, what we did with that was already decide that we could use one of the smallest meshes with 100-kilometer margin and 30-kilometer size to be our test case. What we've seen that in this cost example here is that we are not using parallelization or GPUs. So we are only distributing the tasks by doing simulations daily instead of doing the full simulation. The benchmark validation was done in 50 sites around the globe. So 50 measurement locations that have different characteristics, different terrain, ones are in the forest or offshore, and all of them were done using the same Mpass mesh that we selected before. And what we did was run both Mpass and the equivalent Wharf with and without nudging. Here we can see some of the results for all the sites for the wind speed, the bias, signed and unsigned. And one of the clear things we can see that also came in the test site is that all modeled simulations give way better results than using the reanalysis 30-kilometer data. And what is curious of these slides is to see that Mpass is consistently doing better than Wharf. So in almost all situations, almost all sites, Mpass was doing better than Wharf. But that the nudging option made the Wharf simulations be better than the Mpass one. And this is something that happens with the bias, but we also see it for the correlation, like Wharf with nudging is performing better than Wharf and Mpass, okay? And also for the root mean squared error. So the conclusions of this work that we have presented today show that this mesh generation strategy that we presented is robust and gives results, time series results that can compete against Wharf simulations and that are useful for the wind industry. And this methodology to produce equivalent Wharf simulations is giving the framework needed to validate and test these cases. But I think next comes a presentation that talks more about how to find these equivalent Wharfs and Mpass physics. So I'll be very interested in hearing that. And one of the things that the big questions that goes for the future and for further work is to see if these results that show that nudging is improving Wharf, we want to check if nudging would improve Mpass too, or if intrinsically Mpass is doing something better than Wharf was doing it, and is able to transport reanalysis to the central region in a much smooth way. So what we are going to do next is to test it to 1 kilometer resolution. That means that we'll need 3 Wharf domains, and this nudging information will probably scatter and will give some insight on that. So the main outcome of the presentation is that with the test we've done, we could now run Mpass confidently for any wind resource assessment application that didn't need very high resolutions, and that we are interested in seeing how Mpass develops in the future, whereas we can go to higher resolutions with some large eddy simulations implementation, or if nudging can be added to the model, or if there are some other techniques that can be included to reduce the computational cost. So thank you for listening to the presentation. If you have any questions or suggestions and want to discuss this topic, please contact me. And now I'm open for any questions that you may have. Thanks.
Thank you. By the way, you are perfectly on time.
Nice.
Dave Stoffer?
Yeah, that was a very nice talk. I have the same question I see Pedro just asked. What type of nudging are you using? Is it spectral, or is it analysis? Is it OBS nudging? What type of nudging in Wharf?
So I'm actually not confident about the specific technical term. So it's nudging which is available in version 3.9, which is not the spectral nudging, and is using the reanalysis information on an hourly basis.
Okay, so
I'm
then
not sure about the technical name.
Yeah, it's just the normal grid or analysis nudging then. And are you doing the surface data as well as the upper air data?
No, I think it's only upper air.
Okay, so no higher resolution data near the surface.
No.
Okay, that would be a good thing to do. And especially if you go down to 1 kilometer, you really should be using, the data. OBS nudging would be better than the reanalysis. But yeah, when you get down to those scales, I wouldn't be using analysis nudging.
But what do you mean by OBS nudging? Sorry.
There is.
I need observations then?
Yeah, I mean, we actually directly assimilate the observations. And so you define basically a correlation length scale. So you have in the horizontal and the vertical and in time, and where you have no OBS, you don't do anything directly to the solution, but it's what we do for finer scale simulations. Otherwise, if the reanalysis isn't very good because it doesn't have much observational information, you're relaxing the model to an inferior product.
Okay, I'll take a look into that. Thank you.
Okay, Marta, there's a comment in the chat and a link that you may be interested in.
Sorry, I lost the chat. Okay, I see it here.
Okay.
Of an impedance of analysis grid nudging in Mpass. Okay, that's excellent. Perfect. Thank you very much for this information. I'm surely going to use it. Thank you.
Okay, thank you, Marta. So last in our morning session here, first morning session is Mei Wang, who will tell us about comparison of Wharf and regional Mpass, ensuring consistent physics configurations. Mei?
Okay, turns out I should have tested my Zoom. Wei, would you mind sharing my slides for me? Apologies. Need some permission. Try again. Did it work this time? No.
Did it come out?
Let's try again.
Okay.
Oh, did it work? I think it worked.
Oh, I was.
You're not full screen yet, though.
Okay, there we go.
All right, great.
Better? Great, thank you. Sorry about that. All right, hi everyone. My name is May. I am from the Mesoscale Microscale Meteorology Lab here at NCAR. And so, yeah, today I'll be talking about our work on the comparison of Wharf and regional Mpass, and more specifically ensuring that consistent physics configurations are used between the two models. This is definitely a group effort, so all the collaborators are listed here, and I would like to give special credit to Ming Chen, who basically did most of the work presented here today, as well as Laura Fowler for providing a lot of the bug fixes that I'm going to show today as well. Of course, I'm having the same problem that I think some folks were having. Oh, there we go. So just a brief description of the motivation here. As you all know, and the last speaker has clearly demonstrated that the regional configuration of Mpass has been available for some time now, since Mpass version 7.0. And our question is fairly straightforward. Essentially, it's how do initialize short-range numerical weather prediction forecasts in the range of 2 to 3 days forecast lead time from the two regional models compare? And as you all know, while the model governing equations and the time integration scheme are very similar between Wharf and Mpass, there are differences in the two models. Notably, the mesh and grid configuration, so the computational mesh in the models, but also the physics options and the configurations as well. As Laura Fowler had alluded to in her talk on Tuesday, one version of the physics suite in Mpass does not directly relate to a specific version in Wharf. So we're going to spend some time talking about that today. But first, the basic configuration of the experimental setup. These are our Mpass domain and the Wharf domain here shown. We're using the GMTED 2010 data set for the terrain and the MODUS 20 class data set for the land use type for both models. And you can see that our domain covers basically most of North America. This is set up for nominally 15-kilometer mesh spacing here. And of course, the other difference between Wharf and Mpass is the vertical coordinate system. Mpass uses the geometric height and Wharf uses the mass coordinates. So some efforts have also been put into trying to best align these model vertical levels. They're not going to match exactly, obviously, with time varying model levels in Wharf. But you can see that we've tried as best as we could to match the thickness of each model levels to be consistent between the two. Like I mentioned earlier, a lot of effort has also been put into unifying the physics in the test suite that we're looking at here in this study. And thanks to Kelly Werner, Dave Gill, and also Michael Duda and Laura Fowler to ensuring that these schemes are pretty much identical or as much as we can in the results. So the physics suite that we're looking at here is the Mesoscale reference suite in Mpass. This is actually a pre-release version 6, so it's kind of in between version 6 and version 7, which is why there is the regional configuration capability in here. And then also the Mesoscale reference Mpass physics suite is equivalent to the tropical suite in Wharf. And so I won't list the physics schemes, but this is basically the physics that are used. For ozone, we set it to use the climatology. We use the effective radii computed in microphysics for the radiation computation. No aerosols are used, and we did turn on fractional sea ice as well as snow albedo, and we turned off gravity wave drag to keep it simple. So we ran basically 15-kilometer forecasts for 2 periods in 2017. These are forecasts initialized at 0 UTC every 3 days with the quarter-degree GFS analysis forced by 3-hourly lateral boundary conditions from the GFS forecast. So we ran for 2 periods, as I said. One is in the spring period between April and June, and the other is for a winter period between February and March. Highlighted here are 2 key differences that we've noticed in our experiments. One is in the precipitation forecast during the spring period, and the other is the near surface temperature forecast over the winter period. And this is basically coming out from a detailed analysis that Ming did, looking at the simulation, comparing the simulations from Mpass and Wharf. So we'll talk about the precipitation forecast first. So one thing when we look at precipitation forecast, trying to figure out where the difference is coming from, we could look at the moisture budget. So shown here is the total QV tendency and the top panel from Wharf over for a 72-hour forecast initialized for one of the days during the spring period. The middle panel shows the total QV tendency from Mpass, and the bottom is the difference. And you can clearly see that between 18 and 0 UTC, there's the difference that we're seeing between the two models. And then we can further decompose this QV tendency into its components. So we have the sources coming from the microphysics, the dynamics, and the cumulus and PBL scheme. And these are showing here are the differences between the two models. And you can see here that if you compare the total tendency difference between the two models, most of the differences can be attributed to cumulus scheme. Of course, there is interactions with the microphysics as well as the PBL. So that led us to kind of focus more on the cumulus scheme. Like, could there be differences in the code from the cumulus scheme between the two models? Well, it turns out they were actually indeed identical, and they were as expected, but the differences were actually due to the input to the cumulus scheme. We found bugs in Mpass in the computation of the QV and theta advection tendency forcing terms that are being used as input in the cumulus scheme. And this is not just for Nutica, but it's also relevant for the Brel-Freyeda scheme. And so with the modification that we made, you can see that these differences essentially are much more reduced. And if we rerun these 15-kilometer precipitation forecasts again, showing here again is the domain average precipitation with forecast lead time. These are averaged over all of the forecasts that we ran for the spring period. After the fix, you can now see that the domain average precipitation matches a lot better between Wharf and Mpass. So now moving on to near surface temperature forecasts. These are averaged 2-meter temperature forecasts from Mpass in the top row. The middle row is from Wharf, and the bottom is the difference. And each column shows 24-hour forecast, 48-hour forecast, and 72-hour forecast. And you can see that the difference here is that Mpass is persistently colder, has colder near surface temperatures than Wharf, especially noticeably over the Rockies and also over the Hudson Bay area. So looking at near surface temperature differences, the one thing we looked at was the energy budget. And so if I'm going to highlight some of the differences that we have found by diagnosing these differences. Here on the left plot here, I'm showing Mpass top-down shortwave radiation. So you can see that these are at 0 UTC, 3 UTC, 6 UTC when it's nighttime, and then 12 UTC, 15 UTC, and so forth. And then if you compare it with Wharf, here I'm showing the difference plot here, you can see that Wharf essentially, there's a lag in the phase here. And looking deeper into the code, we realized that the computation of the solar zenith angle that is used to compute the shortwave radiation is a little bit different between Wharf and Mpass. And essentially the definition of the local time, which in the code it's called XT24, for calculating the cosine of the solar zenith angle were indeed different. So we changed Wharf's formulation to follow that. That was done in Mpass. And here is the result for an example forecast. So this is at 0 UTC, so shortwave. We have these sunlight basically over the west of the Rockies. And before, here again, we see this persistent colder temperatures in Mpass comparing to Wharf. And with the fix, or the change, I should say, in Wharf, you can see that these basically eliminated these colder temperatures in Mpass, or the difference, eliminated the difference. But as you can see over the Hudson Bay area, we still see a lot colder temperatures in Mpass comparing to Wharf. And so that led us to look into more into the snow conditions like albedo, and uncovered a series of more bug fixes. So first is the snow albedo in Mpass. Essentially, there was a bug in the initialization of the annual maximum snow albedo variable over sea ice points. On the left here, we can see Wharf. Indeed, it is correctly initialized over the Hudson Bay area, and then indeed Mpass that was missing. And so with the correction, we can reduce this or basically eliminate this difference here. Another thing that we kind of noticed through this investigation is that the default sea ice albedo value in Mpass was a lot higher than that used in Wharf. And so we made it consistent with Wharf. And so again, At 0 UTC, this is the initial time here from a snapshot of one of the forecast runs. The differences are certainly reduced, but you can see that after the forecast has started, the difference pops up again. And further investigation, we realized that the default sea ice albedo option in Mpass was set to option 2 by default, which means that the user should provide the input albedo, but that option is not available. And so what it should have pointed to was option 0, which is using the default snow albedo value. And with that change, you can see that now our albedo between Mpass and Wharf matches nicely over the Hudson Bay area. But looking at the albedo also sort of highlighted these little speckles around the Hudson Bay area in Mpass that wasn't present in Wharf. And that actually helped uncover another subtle difference where that the sea ice definition, the threshold that was used in Mpass was different from Wharf. So in Mpass, it was set to, the threshold was 271 Kelvin. So essentially when the sea surface temperature is colder than 271 Kelvin, it would turn the water in these lake areas, especially into sea ice. Whereas in Wharf, since version 3.5.1, the threshold was set to 100 Kelvin. So it takes a lot colder temperatures to turn that into sea ice. So we have now switched that threshold in Mpass from 271 Kelvin to 100 Kelvin to be consistent with Wharf. And with all these changes and also the change in the computation of the solar zenith angle, you can now see that the 2 meter temperature difference is looking a lot better. You can see the reduction of the colder temperatures in Mpass, west of the Rockies, and also over the Hudson Bay area. I'm showing here on the left here is before all these fixes, and on the right here is after all these fixes. So you can see that the temperature differences are certainly reduced. So in summary, a lot of effort has been put into unifying the Wharf and Mpass physics, as well as through this process of comparison, it uncovered a lot of subtle differences in the model physics configurations. And any similar effort and this effort would really greatly benefit from a shared physics repository. That was the focus of the talk by Laura Fowler on Tuesday, as that would be a great starting point. And that was our starting point for this work, as well as to have a common physics to start with. And then, of course, we have to also unveil a bunch of subtle differences that I had shown just now. This is a summary table of all the changes that we have made to the two models. And certainly some of these changes, especially for the Mpass ones, will be in future releases. The next step, obviously, we will have to rerun the 2 periods with these model changes that we have uncovered. And then also we have conducted similar tests of the convection permitting resolution. And this is an example of the runs that we're looking at. So the square box here is our planned Wharf 15 kilometer domain. And then inside we have a 2-way nested Wharf 3 kilometer nest. For the region Mpass mesh, we have this circular domain here going from 15 kilometers, nominally 15 kilometers mesh spacing in the red regions, refining down to 3 kilometers. And we'll be basically doing a similar investigation for these convection permitting forecasts. Yeah, and with that, I'll take any questions. Thanks.
Thank you. I have to ask you about the solar zenith angle. So is there a bug in Wharf regarding how it calculates local time?
That's a good question. So the difference is that the Wharf has an equation of time term. I probably might not be the best person to answer, so someone, if you want to chime in, feel free. But basically, it's a difference of that term, and in Wharf, we removed it. Basically, Mpass doesn't have that equation of time term. Whether it's, I don't think it's incorrect, it's just a different way of formulating that solar zenith angle.
Okay.
Does that answer your question?
I think I'm confused, but I'd like to know more about that.
No, I could help. The equation of time is in Wharf. It's been there for a few years now, and that's just like a 15-minute. It's a seasonal change that varies plus or minus 15 minutes from the solar time, and Mpass didn't have that. So I think what they did is turn that off in Wharf for the comparison, if I understood the test correctly. But ideally, you'd add it to Mpass as well.
Okay, I'm sorry, Jimmy. So
Yes.
Wharf is not correct?
No, Wharf has the equation of time, but Mpass didn't.
Oh, so so Wharf was changed to be like Mpass, but Wharf was more correct.
Yes.
Okay. All right. Thank you. So in the chat, I see there are lots of questions.
Okay.
Okay, and
Do we have time for that?
well, we've eaten into the break, so I'll let weigh in here.
Yeah,
So
continue the
Pedro asked-
discussion. Yeah, continue the discussion. If someone want to take a break, please feel free to do so. And yeah, I think it's a good discussion. Let's do it.
Okay. Pedro asks about the zenith angle as well. Okay. Koichi asks, what was the bug of input QV and theta tendencies to cumulus schemes fixed in newer versions of MPAS version 7?
I believe it's not in there yet, but I think there is a pull request for it. If someone has more updated information, please correct me, but I believe it's not in the current release.
Okay.
That's correct.
So it's not in the current release.
Not yet.
Okay.
Not yet.
All right, good. I was wondering that as well. Steve Rugg asks, do you envision similar investigations necessary as more physics packages get added to the shared physics repository?
I think as more physics suites get added to the shared physics repository, that could be a useful exercise. But I think the goal here is to demonstrate that they perform similarly, and they do for this physics suite. I think it would make the task a lot easier with a shared physics repository, but making sure the configuration is the same as we see here outside of the physics schemes could also be a tedious task. So I think based on this demonstration, it's, in my view, it would be sufficient, but I think it's really up to the user.
Okay. Wayne Angevine comments, this kind of work is not very glamorous, but extremely important. I'm sure there are more bugs to be found, and I'm sure a lot of us are thinking, we're glad you're doing this. Okay. Oh.
Well, yeah, again, credits goes to Ming Chen, who did a lot of this work, and the whole group as well.
Okay.
Appreciate the comment.
Alan Rosales comments, can we say that MPAS interprets the physics better than Wharf?
I'm not totally clear what that means. Did you say interpret the physics?
Yes. So maybe what is meant is handling the physics better than Wharf. Or implementing the physics.
I don't think that it necessarily says that. I guess the focus here is to make sure that they're doing the same thing, before we evaluate them and say which model is better. Like, we were trying to basically demonstrate that, there are lots of steps before, we could evaluate and say which model is better, and yeah, ensuring the physics configuration is important.
Okay. So there's some more supportive comments in the chat. There's also a question, could something be relevant here regarding the mesh regridding for MPAS Wharf regarding the differences?
That's a good question. I think once we have rerun the 2 periods with these model changes, we could maybe see if there's more, based on those one forecast result that we've seen, or a few forecasts that results that we've seen. The solutions are pretty similar. So, but you do see that around the edge that we see differences, and obviously it's due to the mesh configurations and differences there. Yeah, I guess to be found. I guess to be confirmed.
Okay. All right. Thank you very much for an interesting talk, and thanks to all of the speakers in this session.
Okay, so now we're a little bit over time, and let's come back in at 10:35 to start the next session. You're free to take your own break, but let's start the next session at 10:35. Thank you.
And if anyone in the next session wants to practice or test sharing their screen really quickly, I'll stay here. So just let me know. Just speak up and let me know.
Hi, Kelly.
Hi, Dorita. How are you?
Fine. Nice to meet you online.
Yes, I haven't seen you in so long.
Right. Yes, since 2019.
Wow.
Yeah, I left and then the COVID arrived.
Yeah.
Yes. So yes, I would like to see if I can share my screen.
Okay, go ahead.
Okay, so let me see. Okay, one moment, share screen. So, do you see my presentation?
I do.
And if I do now, and now, two?
Yes, now it's in full screen mode.
Okay,
Yeah.
so it seems to be working.
Yes,
Thank
it
you.
looks good. You're welcome.
Great.
Hi, Kelly, can I try?
Yes, go ahead.
All right, thank you. Are you able to see it?
I see your screen, yes.
So now it's full screen, correct?
Yep, and it looks good. See, make sure you can advance and everything. Yep.
Yeah, looks like it should be working.
Yep, it looks great.
Thank you.
You're welcome.
Can I try to?
Yes, definitely. Go ahead.
Oh,
I see your screen.
it's full. Okay.
Yes, it's still not in full presentation mode.
Right now.
I'm still seeing the full PowerPoint. If you go, let's see. Unfortunately, I can't read the. Yep, that looks good. Now it looks right.
Okay. Thanks.
You're welcome.
Hi, Kelly. Can I try too?
Yes, sure.
All right. Can I see it?
Now I see it. I see your screen.
All right. So, all right.
And now it's in full.
All right. Thanks.
You're welcome.
Hi, Kelly.
Hi, Rosie. How are you?
Good. How are you?
Good.
Can I try as well?
Yes,
Do we have time?
absolutely.
Okay. Okay. Looks like.
Delaying a little. Uh-oh. I'm going to stop sharing.
Right. Let me. It's a PDF, so I think I have to put it in full screen first and then. Or let me just share my entire screen. Yeah. Oops. You should still be able to see it. Is that
I see it correctly now. I see it
okay?
in presenter
Great.
mode. Make sure you can advance.
Yeah.
Yep.
Okay.
Looks good.
Great. Thank you.
You're welcome. So Jimmy, everyone has tested their slides except for Mark Seedfeld. He's here. Don't know if he's like listening right this minute. But everybody's here and ready, I guess.
I can do the test.
Okay, yeah, go ahead real quick. Looks good. Yep.
Thanks.
Okay, so everybody's ready then, Jimmy.
Shall I start now?
Yeah, sure, go ahead.
Okay, so welcome to the last session of the workshop. The next talk is impact of climate change on heavy precipitation events in Eastern Mediterranean. And it's from M. Arman. So if you can share your slide, go ahead. Thanks.
Is that okay?
Yes.
And can you hear me well?
Yes.
Okay, so thank you, Jimmy. I'm going to present a work that we did at the Hebrew University, mostly led by Moshe Armon, a PhD student. And we talk here about heavy precipitation events in the Eastern Mediterranean and what we call insights from event-based storylines. So high precipitation events can cause natural hazards such as flash floods, urban floods, landslides, debris flows, but they are also an important resource for recharging groundwater and surface water reservoirs. And different rainfall patterns during these precipitation events cause different hydrological responses. It is important for us in a semi-arid area to be able to accurately represent the rainfall in this type of events because it is crucial for detecting and predicting changes due to climate change. And the understanding of the specific interactions between the rainstorms and the catchments is critical in small watersheds, as are those over Israel. So the objectives of our study is to characterize rainfall patterns during high precipitation events based on high resolution radar data. We looked into 41 cases. We also, as part of this study, evaluate the skill of Wharf at the convection per meter resolution, its skill in simulating these patterns. And further, our aim was to identify and quantify changes in these rainfall patterns induced by climate change and try to examine, to do an examination of whether some common changes emerge over a variety of high precipitation events. So from the meteorological point of view, from our methodology and data, from the radar point of view, we have a data set of 24 hydrological years that extend from September to August. And we are talking about a non-Doppler C-band weather radar with an effective range of 185 kilometers. We can see here its location and the radius of detection. on top of the contours of seasonal precipitation over the area. And we have used a fixed ZR relationship to estimate QPEs. And we produce these QPEs at 1 kilometer resolution and a temporal resolution of 5 minutes. On the other side, we have the Wharf model, which we run in 3 nested domains at 25, 5, and 1 kilometer grid sizes. We use two-way nesting, 68 vertical levels. The finest domain, as I mentioned, is at 1 kilometer. For historical events, we use the ERA interim reanalysis for initial and boundary conditions, spin-up time of 24 hours, and we simulated the 41 high precipitation events that we chose from the radar data. And here you have the summary of the physics schemes that we chose to use. So our aim, as I said before, is to understand what are the expected changes under climate change. So first of all, we have this radar data for the events. And for these 41 events, we use reanalysis, as I mentioned before, and run the model. And we compared Wharf simulations to radar data. And in fact, here I have an example. It reproduced very well most of the events, except for those that were very localized. So what we want to do next is to insert into this reanalysis data that is initializing and forcing Wharf the signal from climate change. And to do so, we use the so-called method of pseudo-global warming. And we want to see how these Wharf simulations will look like. So what the pseudo-global warming method means is that we take from global models the average of all sorts of variables on a monthly basis, projected from the end, projected for the end of this century, and subtracted it from the end of the average of the end of the last century. And this difference, or delta, was applied to our initial and boundary conditions. And except for this, all other fields were kept the same as in the reanalysis. We use CMIP 5 and the RCP 8.5 scenario. So we performed changes in pressure, wind, temperature, and moisture, and they were applied to the corresponding grid cells in the model and vertical levels. And then we ran these 41 events and analyzed the results in comparison to the historical runs. We see here an example of changes over the domain in temperature. Average changes in temperature were about 4 degrees. And we can see here an example of profiles from reanalysis and the changes that were added. So here we see the overall plot for all historic events that we run. And here we see it, the total rainfall for the simulations that were done with the pseudo-global warming method. And what we can summarize is that we see a decrease in rainfall accumulation of about 19%. Here, the spatial average was 485 millimeters, while here it was 600 millimeters, while here about 500 millimeters for 90. We also see that the area of rainfall is contracted after we apply the pseudo-global warming changes. And here we see the difference in millimeters and in percentage with the gray lines showing the statistical significant areas. And we can see that the wetter areas of the region are the ones in which the precipitation decreases most severely. This plot summarizes rainfall accumulation and the differences between future and historic rainfall accumulation, area, duration, and rain rate for every one of the 41 events. And we are also signaling here the average values. And the main message from this plot is that while the rainfall accumulation, the area and the duration diminishes in all the events almost, the rain rate increases in most of them. So in summary, what we saw from the rainfall during high precipitation events in future climate is a decrease by about 30% on average in the rainfall, with 36% decrease over land. But the rain rates get higher by about 15% on average, and even 22% for local and short duration rates. The events, as I said, become also shorter by 9%, and the rainy area is much smaller, a 40% decrease for 0.1 millimeter threshold. So a Wharf model proved at convection permitting high resolution to be useful and capable of simulating most of these events, except for some short and very localized storms. And it's nice that a weather forecasting model could help us in climate applications. So the future maybe looks like these clouds, while most of the area can be covered by shallow clouds. There will be some smaller areas that will have more pronounced, more developed clouds, and which will give more intense precipitation over a very small area than we expect today, than we have today. So these are the two papers that summarize this work, and thank you very much.
Okay, thanks, Dorita. I see one comment in the chat that this is very interesting and seems to beg for an ensemble of simulations. I guess that would be
okay. So so let's go to the next. So what we took was mean values of these changes, of those delta changes between the large scale in future and in past climates. So we are taking these changes are the average over all these models. So we are not taking the spread in these simulations, but the signal on the mean changes coming from all these models, it is taken.
Thank you. I have a comment myself that the PGW method, I've seen it applied in North America and Africa, and both those places you get more rain in the future climate. So this is the first one I've seen of a region where you expect less rain in the future climate. I think this is
right.
The expansion of Hadley cell, so generally the Mediterranean area. Is that
yes, and we are investigated the meteorological reasons, and some of the reasons that we see also in the large scale is that most of this precipitation is due to Mediterranean cyclones. Their trajectories are northern, so we are getting less in future climate of these cyclones. Also, the winter sea surface temperature, land surface temperature gradient is seen to be diminished in future, and this is also affecting. So so these are some of the reasons that we have analyzed. So these are some of the reasons.
Okay.
Okay, now thanks, Jimmy. You can ignore my question.
Well, that was the same. Somebody asked the same question as I did.
Okay, okay, cool. Yeah, I have more simulations in which we have, for example, okay, the pressure gradient in the surface is also expected to be more shallow. And also we did some factor separation, and what we separate dynamic, thermodynamic, and the synergy between them. And the synergy between dynamic and thermodynamic factors seem to play a more significant role in the degrees that even each of these group of these factors independently. So, yeah.
Oh. Okay, so clearly you've done a lot more analysis. Okay, thank you.
Yeah.
I think we have time for one more question if anyone has one. Otherwise, we'll just proceed. Okay, thanks, Dorita. That was nice talk.
Okay, thank you. It was nice to meet you all.
The next talk is by Myra Lins, Assessment of ITCC Types over the Tropical Pacific in the Channel Model. And this speaker is from Brazil.
Hi, can I share my slide? Okay. Oh, let me just. Okay. Can I?
That's okay.
Good. Okay. Well, hi, good morning or good afternoon. I'm Myra Lins, and I'm from Brazil. I study at the Federal University of Alagoas, and I'm going to show some preliminary results about this study called Assessment of ITCC Types over the Tropical Pacific in a Channel Model. But first, I would like to thank my advisors and my co-advisors for the support. Well, let's begin. A tropical channel model is a model based on the weather research and forecast model that combines the main advantages of global and regional models. This type of model uses boundary conditions only at the north and the south directions, so technically completely solving the propagation of tropical waves and allowing controlling quantifications of the effects of extratropical disturbance in the tropics. Because of the limited area, there can be no hydrostatic and have high resolution, capturing the organization of the tropical convections and various scales and influence on the general circulation. As I said, TCM conditions allow simulations to have high resolution than normally in a global climate model. And also the limited area allows to evaluate the climate variability patterns of the tropical regions. Well, the intertropical convective zone, it's one of the most important climatological characteristics in the tropics. The ITCZ directly influence the characterization of the rainfall regime in tropical areas. Nobre and Uvo 1989 related the importance of identifying how long the ITCZ was positioned further south of its normal position. According to the authors, ITCZ is the main precipitation generating system in the northern region of Brazilian Northeast. Thus, it's better understanding of position, structure, frequency, and migration of the daily ITCZ is clearly very important for describing the atmospheric process, and then Earth climate on the global scale, and the importance of how models represent the system patterns. Well, the methodology. The TCM simulations was conducted in the Florida Institute of Technology. Interim was used as the initial conditions. The horizontal grid scale of the ITCZ is 36 kilometers with 41 vertical levels, and the top of the model with 50 hectopascals. The TCM was integrated for December 1st, 2009 to December 31, 2014. But the first month was the spin-up, so this study assists the period of 2010 to 2014. Well, we use the Chen 2008 methodology to separate ITZ daily partners, which consists to make a binary file, precipitation intensity index, H, that is defined for each region for each day. Basically, it's divided in three regions, north, south, and equator, as you can see. So it's calculated if they are more than 25 of grid points with precipitation greater than or equal to 10 millimeters per day, which is the main rain rate in the ITCZ. And we define if the index is 1, otherwise it's 0 for each day. Then we see, according to the definitions of the spatial partners of the ITCZ that we can see in the table 1, if it is north, south, equator, double, full, or weak that day. Also, we use the same assessment with 14 atmospheric generation circulation model from the 6th phase of atmospheric model intercooperation project, a MPAS, which generally shows poor performance in the tropics. And to evaluation the TCM Wharf simulations and the AMIP ensemble were performance against the Climate Prediction Center morphing technically precipitation data that was used as an observed data. And the CMORPH data has 25 kilometers of horizontal resolution, but all data were interpolated into a uniform horizontal grid spacing of 1 degree. Although the initial analysis of this study is for the Pacific, the next results will include the Atlantic, which is very important for the region I live, and also the Indian to individually evaluate the daily partners of the TCZ in these oceans. Okay. Here are some of the preliminary results for each ITCZ partners. First one is for South ITCZ, and we can see the region with the red box. The next one is the Equator ITCZ. It shows the partners of the observed. And the next one is for the North ITCZ. As we can see in this double ITCZ, TCM usually represents North and South ITCZ, like mostly as some of double ITCZ is not. It's not quite just north or just south. And the next one is the full ITCZ, and the last one is the weak ITCZ. But there were no results of ITCZ weak for TCM. Well, the preliminary results shows the TCM Wharf was able to represent the spatial part of the ITZ, but with a more northerly shape from the south ITZ. Moreover, the GCM was unable to predict the weak ITZ. The possible reasons behind such performance of the ITZ in the GCM, it will be investigated in the next phase of the study. That's it. Reference. Thank you. It was a little bit fast, I guess.
That's a very quick talk. I see one question first from Hao-Chin Tan. Is there another way to quantify the ITCC instead of looking at the mean state?
It's a question, or
yeah, do you have? Can you think? Well, he's asking: is there another way to define the ITCC instead of looking at the mean state?
Yes, but which is this way because of the chain methodology.
Yeah, this is a methodology that's used by other people.
Yeah.
And another question from Rosimar. Are there particular times of the year that favor a north or south or double ITCC?
Well, that's exactly what we are working for. We already do that to another model, but specifically in the GCM, we are still evaluating this type of frequency and how exactly it happens in like in July or June. This thing.
Okay, and a question from Wei Wang is, what cumulus scheme do you use?
Oh, I'm sorry. Can you repeat, please?
Yeah, cumulus scheme.
Oh, I don't recall actually, because I didn't run the model, but I think.
So Pallav says it's the Cambridge.
Yeah.
Cambridge. Okay. I think that was all the questions. So yes, thanks for keeping us on time. That was an interesting talk.
Thank you very much.
Bye. So the next one is by Hao-Chin Tan, understanding the role of topography on the diurnal cycle of precipitation in the maritime continent during the MJO propagation. So Hao-Chin.
All right, thanks, Jimmy. Let me share the screen. All right, so how's it going, everyone? My name is Hao-Chin Tan, currently the postdoc in Organic National Lab. So today I'm going to present one of my PhD works, which is understanding the role of topography on the diurnal cycle of precipitation in the maritime continent during a MJO propagation. So before I start, I would like to thank all other authors this year for their support. Thank you. So my presentation will have these contents. I will begin with the background from literature and motivation of the study, then objectives. I will spend some time on the methods and the theory results and summarize my results. All right, the maritime continent. So the maritime continent is a unique mixture of thousands of islands in the middle of Earth's warmest body of water, the Indo-Pacific wormhole. So this largest archipelago on the Earth is well known for its complex geophysical setting, its marine and land biodiversity, and its rich human history and culture. So studies have found that this area plays a significant role in the global weather climate system. The complex distributions of land, sea, terrain of the maritime continent can invoke different scales interactions, which also bring the high impact local events such as extreme rainfall, flooding. So therefore, like predicting the extreme event related to the diurnal cycle, the synoptic weather system, the Madden-Julian oscillation, and monsoons can bring social and economic benefits to this region. So speaking of the MJO, it is the primary mode of tropical convective variability on the intra-seasonal time scale, and it is over the Indian Ocean to the Western Pacific Ocean. So another thing is that 40 to 50% of precipitation in the maritime continent comes from the MJO, which will further contribute to the global precipitation. So the figure here shows the average MGO cloud and wind patterns. We can see that the MGO produce an enhanced area of cloudiness and precipitation over several thousands of kilometers in the Maritime continent, which propagates slowly eastward about 5 meters per second. It is often paired with an area of suppressed cloudiness and precipitation to its east or west. So this enhanced and suppressed areas of cloudiness in the MGO are always associated with an atmosphere circulation that covers the entire tropics. So the numerical model always have difficulties in simulating precipitation and its diurnal cycle over this area, typically because of the coarse grid spacing that are used to represent the complex topography. Studies with high resolution model have shown that the inadequate grid spacing and model physics may cause inaccurate representation of the precipitation and its diurnal cycle in the Maritime continent. So we propose a case study that using the cloud permitting simulations by Wharf and may be able to provide some insights related to understanding the precipitation and its diurnal cycle. So our objective is quantifying the physical process that control the atmospheric moisture as a function of elevations. We also want to investigate the diurnal variation of moisture from a budget perspective as a function of elevation. We focus on a period where a strong MGO event passed through the Maritime continent in April 2009. So figure on the right here is the RMM index. It shows the progression of the MGO in different phases. So it moves anti-clockwise direction, meaning that the MGO moves from west to east. Another thing is that when this index is within the center circle, the MGO is considered to be weak. Outside meaning that this outside of this circle means the MGO is strong. So in that case, this MGO event is a quite strong case. So we use one domain with 4 kilometer grid spacing, 41 vertical levels. The initial and boundary conditions, including the SST for the model, were taken from the ERA interim quarter degree 6 hourly. No cumulus parameterization we use. The microphysics was WSM6 and MYJ for the PBL. The observation for precipitation is taken from the CMORPH dataset. So in order to isolate the role of topography, we designed the control simulation with realistic topography and the flat simulation which use 2-meter unified flatland. Okay, the results. For the mean precipitation compared with the observation, the model kind of underestimate over the ocean and overestimate over the land. So this overestimation over the land may due to the mechanism that related to the boundary layer transfer and the convective lifting, condensation, precipitation. May due to they are not well reproduced by the parameterization schemes. A finer resolution may be able to address this issue. So compared with the control, the precipitation in the flat experiments weakens over the elevated part of Sumatra and New Guinea Island. So over these regions, the precipitation is not enhanced by the cumulus mergers process because the sea breezes that converge from the coasts towards the center of each island are not lifted by the topography in the flat experience. So as a result, the precipitation without topography decreases by 16%. We also examined the timing of maximum in diurnal cycle of precipitation. So the rainfall peaks over the island occurs from afternoon to midnight in Maritime continent. So the distinct feature in the flat compared with control is that the timing of maximum in the diurnal cycle delayed from 1 to 6 hours over the center of the major islands. The right panels show the evolution of diurnal cycle of precipitation. We can see that the phase of precipitation in control is very similar to what from the satellite observations, peaks at 1500 local standard time. So this definitely proves that the phase in the precipitation can be improved by the increase in model resolution, since most of the low resolution simulations have precipitation peaks about 3 hours earlier compared with observation. So figuring here is the relationship between the topography height and precipitation difference between flat and control. It shows that the precipitation differences began to increase on the high topography levels, roughly about 1,000 meters, from 0900 local standard time to 1500 local standard time, which is also the time of the major precipitation over islands. So overall, after the removal of topography, the precipitation is reduced by 50% on the topography above 1,000 meters. So to understand the underlying process that lead to this difference, we built the moisture budget analyze. So to quantify the impact, we conduct the column integrated moisture budget analysis by this equation. So variable in this equations are the specific humidity, the horizontal wind, vertical velocity, evaporation, precipitation, and residual. So the column so the brackets indicate mass weighted vertical migration from the surface to 100 hectopascal. The term on the left is the moisture tendency, and the first and second terms on the right-hand side are the horizontal and vertical moisture advections. So panel in here are the diurnal cycle of moisture budget terms. So the top panels are for all land area, and the right panel is for the land above 1,000 meters. The solid lines for the top panels are for the terms in the moisture budget for the control simulation, and the dashed line for the flat simulation. So the bottom panels are for the differences. For precipitation, it is mostly balanced by horizontal, and the precipitation is mostly balanced by horizontal and vertical moisture advection. So in the flat simulation, the amplitude of precipitation decreases along with the decrease of horizontal and vertical moisture advection. The timing of peak precipitation in the flat also lags of the control by about an hour. Another thing to notice is that the peak of horizontal moisture advection in the control shifts from 1600 local standard time to 1900 local standard time in flat simulation. Another thing we look at is that our case is during an MGO propagation, so meaning that our dominant background wind changed from easterlies to westerlies. The panels in here shows that during the period of easterlies, the diurnal cycle is stronger than during the westerlies, which is consistent with previous studies. The peak of precipitation reduced about 30% during the background wind change. The overall difference between the control and the flat in the moisture budget shows that the difference of vertical moisture advection almost follows the difference of precipitation in both easterly and westerly phases, except that the horizontal moisture advection becomes a little bit more significant in the afternoon hours in the westerly and the easterly phase. So this change caused by sea breeze converges from the coast toward the center of each island in the afternoon. So for areas with topography height above 1,000 meters, the precipitation undergoes like similar diurnal variation from westerly to easterly, but the decrease is less compared with the average of precipitation over all islands. It only decreased about 8%. So the diurnal cycle of the other moisture budget terms almost retains their characteristics with relatively small differences during the change of background winds in the control compared with area of all island. All right, a little bit summary here. So in the absence of topography, the precipitation becomes weaker and the maximum diurnal precipitation is delayed due to the lack of orographic lifting. The areas that were most impacted were areas above 1,000 meters. So with topography, the mechanical and thermodynamical forcing lead to a convergence. So this the absence of this forcing in the flat simulation leads to like 33% decrease in precipitation at 1,200 local standard time, 24% at 1,500 local standard time, and 9% at 1,800 local standard time. The moisture budget shows that without topography, the horizontal and vertical moisture advections are influenced. On higher topography area, the removal of topography can induce 50% less precipitation. Also, the horizontal moisture advection becomes dominant in the afternoon where there's no topography. The schematic on the left shows that the decrease in precipitation during the peak precipitation is 44% from the horizontal moisture advection and 55% from the vertical moisture advection. Another finding is that during the background wind change, the high topography's precipitation decrease less compared with all-land areas. This result shows that the background wind have a larger impact on precipitation over low topography area than those elevated areas. So we hope our 4-kilometer Wharf simulation provides a contribution to understanding the upscale evolution of cumulus into mesoscale convective system that affects the Diurnal cycle precipitation and might have some implication for the parameterization of organized convection in the global climate model, since the convection is neither resolved or fully represented by cumulus parameterization in some modern global climate model. Thank you.
Okay, thanks, Chen. I see one question here from Rosimar. Are you hypothesizing that the reduction of precipitation due to terrain explains the propagation of the MJO past the Maritime continent? The relation, does it affect the propagation of the MJO when you do this?
Oh, so yeah, so without terrain, the MJO propagation, without terrain, the MJO propagation becomes stronger. So,
okay. Does it explain the propagation? Then does the terrain explain the propagation? Because
come again?
Yeah. Does the presence of terrain explain the propagation?
So in this case, the MJO does not so for this case, the terrain does not block the MJO propagation.
Okay. Thanks. I had one minor question on, so the effect of topography, there's two effects really. One is like the diurnal effect of upslope and convergence due to the heating.
Yep.
And the other is just plain forced descent from just having the topography there. In your budget, there should be a way to separate how much of that is just due to the heating versus just forced descent. May not be easy, but do you know which is more important? Is it the presence of the localized upslope heating or forced vertical motion?
So the precipitation differences is mostly from the vertical moisture advection. So,
yeah, it could be forced vertical motion or it could be convective vertical motion.
Yes. So maybe theoretically, like the thermodynamics and the mechanism of lifting, they're both responsible for that, but needs to be more investigation for sure.
Okay, are there any more questions? Looks like there aren't. So yes, thanks, Hai-Chen.
Thanks.
Okay, we go to the fourth talk. So this is Rosimar Rios Barrios from NCAR, three-dimensional structure of convectively coupled equatorial waves in Mpass.
Thanks, Jamie.
Looks fine. Thanks.
Looks good. Okay, thank you. Yeah, thank you very much for the opportunity to speak here at the Wharf Mpass Users Workshop. So my name is Rosimar Rios Barrios, and I'm a scientist here in KIP, and I'll be telling you about the three-dimensional structure of convectively coupled equatorial waves in Mpass atmosphere. And so we're focusing on the tropics because the day-to-day and week-to-week variability is very important. So tropical rainfall is very important component of the global hydrological cycles, and many communities are incredibly sensitive to tropical rainfall variability. So if we have too much rain, it could be a problem, but if we have not so much rain, it can also be a problem, as illustrated by, for example, these two very contrasting figures of agricultural regions in Africa. So it's this week-to-week variability that we're focusing on and trying to understand better, because it can explain a lot of the rainfall that happens in the tropics, but also outside the tropics. However, as it was very nicely put by the authors of this study, we have a lot of difficulties with reliable representations of tropical convection in our global weather and climate models, partly because of the complex hierarchy of interacting scales. And we heard some of those complexities in the previous talk, so it was a nice background for this talk. And there is a myriad of issues that have been identified by the literature. I'm not going into a whole lot of details. I'm listing some issues here, but I'd like to draw your attention to the second bullet point on the left, which is the poor representation of equatorial waves and MJO, which seems to be a very persistent issue in global models. As an example, here's a figure from Diaz et al., 2019. And they're showing Hoffmuller diagrams with time increasing down in the y-axis, and in the x-axis we have longitude. And this is rainfall rate average within the tropical belt from CMORPH as a proxy of observations, and then from 5-day forecast in the middle from the GFS, and on the right from IFS. And so if we look at CMORPH, we see these day-to-day or week-to-week variability of tropical rainfall in the form of zonally propagating disturbances. So for example, we see many eastward propagating disturbances as well as westward propagating disturbances that may be more short-lived. But if you look at the models, we don't see that propagation. In fact, we see nearly stationary rainfall features. So this is clearly an issue, not only for prediction within the tropics, but also outside the tropics. So these issues are believed to stem, at least partially, from deficiencies in the convection parameterizations that these models have to use, as well as our poor knowledge about multi-scale interactions in tropics. So these issues motivate the work that I'm doing, in which I'm asking two questions. First, can explicitly resolve deep convection alleviate some of the modeling issues regarding tropical rainfall? And specifically trying to get at this issue from a phenomenological perspective, what is the sensitivity of equatorial waves and their structure to whether convection is explicitly resolved or parameterized? So to address these questions, I'm using modeling experiments using the model for prediction across scales, or MPAS. I don't have to tell this group what MPAS is, but just briefly, I'll tell you that I'm looking at both simulations of past dates that have been produced by other colleagues at NCAR, as well as idealized experiments, and those are going to be the focus of the rest of this talk. And so those modeling experiments are going to be analyzed by comparing equatorial waves with resolved or parameterized convection to understand what's the difference between those two frameworks. So we're looking at a simplified framework because there is a lot of power in looking at idealized frameworks. So they are not the full atmosphere, but like Rich Rotuno told me that Smagorinsky told him, the model is not perfect, but it gives us a complete data set. So the idealized framework I'm using is called an Earth-like aquaplanet. And I implemented this capability in Mpass. I'm hoping to put it in the community version soon. But I'm going to play this animation to show you what this looks like. On the left, we have an animation of rainfall rate in the colors and outgoing long-wave radiation, or ORLR, in the gray shading. And so, like the name suggests, it's like Earth. So we use Mpass in its global configuration, but I removed the land, the sea ice, and the seasons. And so we have perpetual equinoctial conditions, but we do keep things from the real world, like a diurnal cycle, the planetary rotation, and we do impose a meridional SST gradient. So the underlying SST is fixed with time, but it's zonally symmetric, but it changes with latitude. And in this case, it peaks at the equator and reduces to 0 degrees Celsius at about 60 degrees on each side, on each hemisphere. And the power of this is that we put these conditions on Mpass, and then we run Mpass with model physics from the NWP community. Specifically, I'm using WSM6 for microphysics, YSU, PBL, RNTMG radiation, and the scale-aware TIPK cumulus scheme that Wei Wang has modified. And so as you probably saw in this animation, even though this is very idealized, the results look very similar to what we may observe over tropical oceans, especially over the Pacific Ocean. We have an ITCC that's very active. You may even see eastward propagating or westward propagating disturbances with the naked eye. Those are the so-called equatorial waves. We have the dry subtropics, and then we have a lot going on in the mid-latitudes. And so to get at the question about the effects of parameterized versus resolved convection, I have what I call a hierarchy of experiments, in which I have 3 experiments that have global uniform resolution and use a cumulus parameterization, but they use resolutions of cell spacing of 120 kilometers, 30 kilometers, and 15 kilometers all over the world. And then the 4th simulation, we use the grid refinement capability of Mpass to give us convection per minute resolution where we want it, which is in the tropics between 20 south to 20 north. And then outside the tropics, it smoothly transitions to 15 kilometers cell spacing. So the first 3 simulations are relatively cheap, so they are 3-year long, but the last simulation is very, very expensive, so it's only 4 months long. So we're just gonna focus on the last 100-day simulations day to discard some period from the 3-kilometer simulation for spin-up. And so there is a lot that we can take a look at in these simulations. So I'm just gonna walk you through a summary of some of the results that we have found. And so the first key result is that resolved deep convection captures more tropical rainfall variability. And I'm showing you a quantitative analysis of that. This is essentially a histogram in which in the x-axis we have each of the experiments, and in the y-axis what we have is the total variance of rainfall rates between 20 south to 20 north. So this is how much rainfall is varying throughout those last 100 days. And what we notice is that if we look at the first 3 bars, which are the 3 experiments with parameterized convection, they're strikingly similar to each other, even though the grid spacing is very different. So this is telling us that it's the cumulus parameterization likely driving a lot of the rainfall variability in these simulations, which is not too surprising, but it's almost like a step function once we go to convection per minute resolution. Specifically, the 3-kilometer experiment has twice as much variance. That is a lot more variability in terms of the tropical rainfall than the other experiments. And so a lot of the rainfall variance is driven by these equatorial waves. So we can specifically calculate this quantity, but just for the waves. And so this is what is shown here. So light gray is that variance that it's only associated with Kelvin waves. Medium gray is only associated with advective disturbances, which are like equatorial Rossby waves or easterly waves. And the dark gray is inertial gravity waves. And so in all of the experiments, you see light gray, and that's because Mpass turns out to be a very Kelvin wave friendly model. We tried to do sensitivity experiments to get rid of the Kelvin waves, and we couldn't do it. So it happens to that regardless of resolution, if you're interested in studying Kelvin waves, regardless of resolution, you're likely going to get them, at least in the aquaplanet setting. But if you pay attention to the other 2 kinds of waves, there's a lot more variance in those waves at 3-kilometer cell spacing than in the other simulations. And that means that the 3-kilometer experiment, which with its resolved deep convection, it's capturing a lot more of those westward propagating, very small scale and very short-lived waves. So we can take a look into more detail. As I said in my title, we're interested in looking at the structure of these waves to try to understand better why are we getting more variance with the 3-kilometer experiment and resolve deep convection. And so it turns out that all of these experiments capture the overall rainfall structures, but the key difference is that the waves are stronger when deep convection is resolved. And we can see that result in these plots, which are showing rainfall rate anomaly with respect to the time and zonal mean as a function of wave phase. So just think about this as an east-west cross-section in which wave phase 5 is at the convective peak and wave phase 1 is at the convective valley or the convective inactive region. So this is composite for many, many, many waves that I tracked in the simulations. And so we take the composite and take the mean and after subtracting the zonal timing. And so the purple line is the composite for the 3 kilometer experiment, and pink and green are composites for the convection for the experiments with parameterized convection, which again, like before I said, the 15 and 30 kilometer experiment are strikingly similar to each other. I have conservatively interpolated everything to the same grid so that we're more or less comparing apples to apples. And even though I'm doing all of that, the 15 and 30 kilometer are very similar to each other for all of these 3 waves that we're considering. And the main difference is that the 3 kilometer experiment is producing heavier rainfall at the convective peak, so stronger waves, but also the anomaly at the convectively inactive phase is more negative. So the resolved deep convection is not only capturing stronger waves, but it's also perhaps capturing like a sharper transition between the convectively inactive and the convectively active phase. So of course, the question then becomes, why is deep convection, why when we have resolved deep convection, we have stronger waves? And so our hypothesis is that there are different rainfall rates resulting from differences in the vertical structure of these waves. And that's because to a first approximation, we can say that the rainfall rate is approximately equivalent to the vertical flux of water vapor, to the upward flux of water vapor. So what we're gonna do is that we're gonna use this same wave relative phase, and we're gonna compare the vertical structure of water vapor and upward motion. And we're gonna compare these simulations against the climatological composite from ERA5 for waves only over the Pacific Ocean, where the aquaplanet is most similar to the real planet. And so here is what those composites look like. On the left, we have the 20-year composite from ERA5. In the middle, we have the 3 kilometer experiment. And on the right, we have the 15 kilometer experiment. Now on the y-axis, we have pressure. So this is a vertical cross section. And again, the wave phase in the x-axis, think about it like an east-west. So the key point here is that all of these experiments capture the overall consistent structure. So we have a westward tilt with height of the vertical motion as we expected, but there is much stronger ascent and descent when we have resolved deep convection. Now, when we look at the composite specific humidity, we start to see some critical differences between the parameterized convection experiments and the 3 kilometer experiment. So in ERA5, we have essentially this westward tilt with height of humidity anomalies, and they're more or less coupled with each other. We have a strong anomaly in the mid levels and a strong anomaly in the low levels, and they are located east to west. When we look at the 3 kilometer Mpass, mining some details, we still see that coupling between those anomalies. But in the 15 kilometer experiment, we have a sharp dry layer, and that happens to be below the melting level. That is essentially decoupling the low level moisture anomaly from the upper level moisture anomaly. And so there's this dry layer present, and it so happens to be that also within that layer, we also see stronger temperature anomalies when we have parameterized deep convection. And so I'm running out of time, so I don't want to take so much more time, but I'll just conclude by saying that the potential explanation is that there are different heating profiles. So these are essentially diabatic heating profiles during the convectively active phase of the waves. And what I like to draw your attention is to this very sharp gradient below the melting level in the green and pink lines, which are the Mpass experiments with parameterized convection. This is for Kelvin waves on the left. We also see it on the right for inertial gravity waves, but we don't see that very sharp contrast neither in soundings from Dynamo nor in ERA 5 reanalysis or in the resolved deep convection experiment. And I'll skip through the next slide, but I'll just mention to you that we're thinking that this is related to the parameterized melting, because when we turn off parameterized melting within the Titke scheme, which is the green line now, that sharp gradient is gone. So the answer, of course, is not to turn off melting, is that we do need to see how the melting is parameterized and what we can do. So I'm just gonna put up the summary slide here in the interest of time and just conclude by saying that I have also looked at realistic simulations, not just Aquaplanet, and the results are still very valid. Thank you.
Okay, thanks, Rosamar. Are there any questions? I don't see any yet in the chat. So you mentioned something about Kelvin waves, having a lot of Kelvin waves. Is there any reason to be worried about that, or is it expected on an aquaplanet? Do you compare with other models, for example? How do you?
That's a good question. So, so when we look at it from the realistic simulations, it's very comparable. So we do see that the frequency of Kelvin waves in the Mpass experiments is consistent with what we observe. When it comes to the aquaplanet, the results vary a lot from one model to another. For example, I compared these against 6 CIMEP models that were run in aquaplanet mode, and I think only one of them also had Kelvin waves. The others had many other solutions, but not Kelvin waves.
And there's a related question in the chat that I just saw, which is whether other physics would have a similar, would similarly have a lot of Kelvin waves. Do you think it's sensitive to physics? I guess is that question.
So we did an analysis in the 2020 paper where we used the Gerl-Freitas convective scheme. We used Thomson microphysics. We even reduced the vertical grid spacing, and we still found Kelvin waves in the models. So we think it has to do something between the physics and dynamics coupling that for some reason, when you put these aquaplanet simulations, when you put the SST at the equator, it induces an SST, the ITCC, there is heating within the equator. And so it's expected from theoretical perspectives that that heating should lead to this kinematic structure associated with Kelvin waves. So it seems that the model is doing what it's meant to do. Of course, we don't have an aquaplanet in real worlds to see if Mpass is producing too many Kelvin waves, but at least it makes sense that it's producing them.
There's a question from Pallav about how it performs for MJO. Does aquaplanet have? No, go ahead.
Yeah, that's a good question. So I do not have an MJO in these aquaplanet simulations. And when it comes to aquaplanet simulations, whether the aquaplanet produces an MJO or not is very tricky, because there are some studies that argue that you need to have a zonal asymmetry to be able to have the MJO. And if you think of the real world, we do have a very pronounced zonal asymmetry with the worm pool. So it makes sense that if you put a zonal asymmetry, you get an MJO. But when you have a zonally symmetric SST, we don't expect an MJO. Some studies argue that they do get an MJO, but it seems to me that it's more like a very slow propagating Kelvin wave, not necessarily an MJO. But other people may have a different opinion than me.
Okay, thanks. I see there are some more in the chat that you could answer separately on the chat as we have to move on. Thanks, Rosemary. Okay, so the second to last talk is Pallav Ray, an improved simulation of mid-latitude climate in a new channel model compared to contemporary GCMs. So Pallav. Okay, good.
Okay. All right, thank you, Jimmy. I'm going to talk about a new channel model that is built for the mid-latitude and its performance compared to observations and contemporary GCMs. Much of the work was done by Sinjo, my graduate students, with contributions from rest of the authors. So the channel models are zonally global, but meridionally bounded. And the meridional boundaries can be put according to the user needs. So previously, tropical channel model have been used by many authors. So for today's talk, I'm going to introduce a mid-latitude channel model for the Northern Hemisphere. So the main advantages of channel models are that it can have higher resolutions than typically it is possible in a GCM. It also needs fewer lateral boundary conditions because channel models only need 2 lateral boundary conditions in the north and in the south compared to 4 boundary conditions that are needed in a standard regional model. And the last point which we are going to utilize is that the channel models can control the influence from low or high latitude through meridional boundaries. So the major motivations of this talk is to explore whether a mid-latitude channel model that's built based on Wharf can outperform contemporary atmospheric GCMs, and then to explore the geographical regions where tropical forcings, primarily from the MGO forcings, are most dominant in modulating the mid-latitude circulation anomalies. Okay. So this is the setup of the model. What you see here is a mid-latitude channel model for the Northern Hemisphere, starting from 26 degrees north to 60 degrees north. You do not want to go beyond that because we are using Mercator projection domain, so things starts to distort. And the horizontal resolution that I'm using is 1/3 of a degree, and the simulations were run for 49 months. However, we are actually not utilizing the first month, and then all the evaluations are conducted for 4 years. One thing you notice for the mid-latitude is the zonal asymmetry due to land-sea contrast and also because of the topography. Similarly, you also see very steep gradient in meteorological variables. An example is given here in terms of sea surface temperature, and you can see that within this 30-degree or so latitude, the SST decreased from roughly about 296 to about 276. So it's almost 20-degree decline. So overall, because of the gradient in meteorological variables, mid-latitude climate, mid-latitude area is a region where eddies are very dominant in the winter hemisphere, so winter time. So that is something we are also going to evaluate for MCM. So we are using ER interim for as observations, and then GPCP and TRIM for rainfall. For atmospheric GCMs, I'm using 20 ME5 models. So these are all atmosphere-only models. The horizontal resolutions of those models range from roughly about 20 kilometer to about 300 kilometer. So for comparisons, all data were interpolated to 2.5-degree grid boxes and standard 17 vertical layers. And the comparisons will be made against multi-model ensemble, which is based on all 20 ME5 models. Okay. So two results are in 2 parts. First, we evaluate the performance of the MCM, and then we will explore the role of the MJO on the mid-latitude circulation using this MCM. So this is observed precipitation at the top panel here, averaged over those 4 years. The middle panel is from MCM, and then the bottom panel is the ensemble mean from ME. It's clear to see that both MCM and ME captures the overall horizontal structure of the precipitation. However, you notice that the MCM kind of overestimates the precipitation compared to GPCP precipitation. However, GPCP is well known to underestimate heavy precipitating regions. As a result, we looked into other data sets. So what you see here on the right is the precipitation from TRIM for the same time period. And you notice that now the precipitation in TRIM is actually much larger compared to the GPCP and matches fairly well with what we got in our MCM simulation. TRIM does not go beyond 50 degrees, so this part remains blank. So overall, things to note is that there are, of course, observational uncertainty. However, it is clear that MCM performs much better than EMIP and EMIP ensemble if you utilize very simple statistical measures like bias, root mean squared error, or correlation coefficient. So next, what I show here is the longitudinal distribution of precipitation bias. So x-axis is longitude, and on the right here, you see precipitation bias. And this gray shading is just the topographical cross-section. So there is a faint gray line which shows zero bias line, and you can see that the red line is much closer to this gray line compared to this blue line, which is coming from EMIP. So it's very, very clear that MCM performs better than EMIP simulation, and in particularly over land. If you look at the 2-meter temperature, then you notice that there is an underestimation of 2-meter temperature by EMIP models, and again here TCM, again here the MCM performs better. So overall, MCM outperforms EMIP for climatology and seasonal cycle, and we have looked into many other variables and processes, and the results are consistent. Now that leads to a second part, which is does the MCM also capture the mid-latitude eddies better than EMIP models? So what I'm showing here is the meridional heat transport by the eddies. So what you're seeing here, total heat transport, which is composed of heat transport by the mean circulation, heat transport by the stationary eddies, and the heat transport by the transients. This figure shows on the left stationary eddies, and on the right is the transients. And only for the winter months, December, January, February, because that's when you know that the heat transport is dominated by the eddies. It's easy to see that the observed and MCM structures are very, very similar for both stationary and the transients. However, when you look at the EMIP ensemble, you notice that the peak in stationary eddy transport has been moved slightly downward and also southward, compared to what you find in observation or in the MCM. Similar results are found for transients where EMIP simulated heat transport is weaker compared to the observation and MCM. Now, next we are asking the question why the MCM performs better than the GCMs. So there are there could be two possible reasons. One is high resolution in the MCM, because it turns out that 18 out of the 20 EMIP models had coarser resolution compared to the MCM. And the other possibility is we are using the observed boundary conditions that can constrain the model simulation. So to test the resolution dependence, what we did is we conducted a new simulation using MCM that has much coarser resolution, 1 degree, and then we compared that simulation against 5 highest resolution EMIP simulations, the average resolution of which is roughly about 0.5 degree. Even this coarser resolution MCM outperforms ensemble based on 5 high resolution EMIP. So that tells me is that resolution was probably not the dominant reason why MCM performed better, and possibly it's because of the use of reanalysis based boundary conditions. Another interesting point to note here is that MCM also performs better than GFDL high RAM, which has been found to be one of the best models for MGO teleconnection. So that tells us that MCM might be well suited to understand the MGO teleconnection simply because it outperforms the best GCM available. So in the second part, I'm going to explore the role of MGO on mid-latitude circulation. To do that, I am utilizing 2 simulations. One I'm calling control, which was ran for 3 months, December 99 to February 2000. Again, covering the winter months, because that's when the MGO teleconnection is dominant over the mid-latitude circulation. And another experiment, I'm calling it a MGO removal, which is same as control, but the lateral boundary conditions are based on annual cycle from the year in terrain, which basically means that we are damping or eliminating the MGO timescale as well as higher frequency events. Okay. So there is a lot of panels here, but we'll focus on a couple of things. The left-hand side is the MCM, and on the right hand, what you see is the ERA interim. And if you look at, let's say, phase 1, you can see that the MCM does a really good job, much better than what I originally expected. Now, the main part that I want you to focus on is, let's say, the northeastern part of North America. So this is phase 4 from ERA interim, when MJO is actually active in the tropics. And that is the time when you actually see a positive or warmer anomalies in this part of the world. And the model was able to capture that very efficiently. Now, if you come to phase 7, when MJO is somewhat inactive in the tropics, and that's when you actually see a reversing sign, particularly in the northeastern part of North America. And you see that the model was also able to capture that. Now, interestingly, it turns out that most GCMs struggle to capture the magnitude of the anomalies. And in a recent paper by Stan et al., who suggested that this error is possibly because of the erroneous MJO in the model. Now, in our case, because we are forcing the model through using the lateral boundary conditions from reanalysis, we are forcing with realistic MJO. So that's possibly the reason why MCM is doing so well at different MJO phases. So basically, the underlying message was MJO teleconnection was very realistic. Now, what I'm showing here is the left-hand side is same as the previous panel from the control, and on the right, I'm using MJO removal experiment. Again, I'm focusing on those two areas. You see that in the control, you have warming, but when we are damping MJO, that warming is actually reduced substantially. Okay, so obviously so this way we can actually quantify the role of MJO on the mid-latitude circulation. On the other hand, if you look at phase 8, when MJO is inactive, when we had cooling in the MCM, we actually see warming in the MJO removal experiment. And I believe that this is possibly because of the high frequency events that were also removed in our experiment. So in the future, we are obviously going to separate high frequency events and the MJO. So with this, I want to summarize that we built a mid-latitude channel model, which is based on Wharf, and it outperformed contemporary GCMs. Even coarse resolution MCM was better than higher resolution EMIC models. And finally, the MCM captures the mid-latitude circulation at different MJO phases and points to geographical regions where we might expect MJO impact to be dominant. With this, thank you everyone for your attention. And if you have any questions or if you want to utilize this model, feel free to send me an email. Thank you.
Okay, thanks, Pallav. I haven't seen any questions in the chat yet. Does anyone have any questions for Pallav? I missed how you removed the MJO. Was it just some kind of time averaging of the boundary condition, or how did you do that?
Yeah, so I think I forgot to mention that. What we did is we utilized 10 or 15 years of ERA interim, and then basically just keep the annual cycle.
Okay.
So only the annual cycle was relaxed to reanalysis.
Okay.
So it's not the best experiment to remove MJO, but this is the first step.
Interesting. Okay, I'm not seeing other questions yet. So, okay, thanks, Pallav. Interesting talk. Well, we'll go on to the last talk of the workshop. And that would be Mark Seefeld, who gets the honor of the last talk. Dynamical downscaling using Wharf in a fully coupled regional climate model.
Very good. Thank you, everybody. Hello, and appreciate this opportunity to share some of the latest work that we've been doing with Wharf in the regional Arctic system model. This presentation is going to focus on an evaluation of dynamical downscaling in the fully coupled model. I want to recognize the co-authors for this project from the RASM team. For this study, we're looking at a fully coupled regional Arctic system model, or RASM, to dynamically downscale decadal simulations from the Community Earth System Model Decadal Prediction Large Ensemble. We're pursuing two scientific questions. How does the downscaled RASM simulation respond to biases in the CSM DPLE driving data? And the second question is, does the use of nudging in the upper atmosphere limit the ability of RASM to develop its own near-surface climate? The key is that the initial lateral and nudging forcing conditions from the CSM DPLE are applied only to the atmosphere above the surface. The surface state and fluxes are provided by the coupled component models and not the source global data set, as would be the case in an atmosphere-only dynamical downscaling. The regional Arctic system model is a limited area coupled atmosphere, land, ocean, sea ice model focused on climate simulations of the Arctic. The component models include Wharf for the atmosphere, and it's Wharf 371, 50-kilometer resolution, 40 vertical levels, 50 hectopascal model top, and then grid nudging of T, temperature, U, and V above 500 hectopascals. Land is using the VIC model, ocean, POP2, sea ice, SICE, and all these component models are coupled together using CPL7 of the CSM framework. RASM focuses on understanding mesoscale processes and the resulting feedbacks that are critical to improved representation of the state of the Arctic climate system. The RASM domain for the atmosphere is this larger domain as highlighted. The blue sort of square rectangle is the POP sea ice domain. Within this, we also use regions to analyze the results, to look at it in terms of location for atmospheric state and fluxes. And so we have the North Pacific, the Central Arctic, and the Lena watershed. So we're downscaling the DPLE data, which uses the CSM version 1.1. This is the same model as the CSM large ensemble. 40 ensemble members were run from a November 1 start for 1954 to 2015. So a total of 62 ensembles. Each member is run for 10 years plus 2 months. However, only 10 members have the required 6 hourly output to force the RASM simulation. The creation of the Wharf input files from the DPLE data followed that of Breuer et al. 2015, including using WPS 371 and NCL scripts with modifications to some of the scripts to work with the DPLE data. The surface and subsurface fields in the Wharf input files were not necessary with RASM being a fully coupled modeling framework. Bias correction was not applied to the Wharf input files from the DPL data for reasons that will be covered later in this presentation. Our experimental setup has 2 RASM simulations forced by reanalyses, error interim, and CFS. These are initialized on 1 September 1979 and run 2018 for error interim, 2020 for CFS. Then we have 10 RASM DPLE simulations forced by 10 DPLE ensemble members with an initialization of 1 December 1985 and running for 10 years plus 1 month. The atmosphere is specified from the driving CSM DPLE data. Ocean, sea ice, and land are initialized from the RASM error interim simulation that was started in September 1979. Additionally, 2 alternate RASM configuration simulations were completed. These are the same as the standard RASM simulations, except replacing the Grell 3D cumulus scheme with Kane-Fritsch, and this is to show the dependence of the results on the configuration of the RASM model. So looking at the results, we're looking at the upper levels, 300 and 500 hectopascal geopotential and temperature. On the left, we are showing the results for the 10 ensemble members that are in different shades of blue, as well as red for the 0-1 ensemble member and 0-2 for the green for the 0-2 ensemble member, as well as in comparison to the RASA era interim simulation in gray. In this, we can see the range of each RASM simulation, and we are selecting the first 2 ensemble members just to do a more in-depth analysis looking at those 2 ensemble members. So on the right set of panels, we're looking at 4 RASM simulations, era interim, CFS, and then 2 DPLE ensemble members. And the RASM simulations are in these solid lines. And then the 4 corresponding forcing data in the lighter dashed lines for each simulation. With this, we can see that each simulation follows that of its corresponding forcing data. And we are also able to see that biases are apparent between the DPLE and the reanalyses. So for example, at 500 hectopascal temperature, all our reanalyses, the simulations, and the source data are at like negative 21.5. Meanwhile, all the DPLE simulations and source data have a bias of about 1 degree Celsius. That is also clear and apparent at 300 hectopascals with our reanalyses, source data, and simulations, and then the cold bias with the DPLE source data and simulations. However, when we look at the lower levels, and so this is 850 hectopascal geopotential height and temperature, as well as sea level pressure and surface temperature, the RASM results are now clustered in the lower levels based on the model configuration or the simulation, and the negative bias that was occurring with the DPLE is gone. So we can look at surface temperature here. All 4 RASM simulations are showing roughly the same surface temperature with a bias warmer than the era interim and CFS source data, and then our cold bias in the DPLE data is still present in the source data, but not in the RASM simulations. We're also able to see that the imprint of the weather, and that being the shape of the curves for the different DPLE versus RASM simulation of the DPLE, follows the same pattern. So you're able to see this imprint of the weather from the DPLE into the RASM simulations. So we could take a look at this in a spaghetti plot of the 5,400 meter contour of geopotential height, looking at it for January 1986. We have the 10 ensemble members, again with red being the 0-1 ensemble member, green the 0-2 ensemble member. And we see this large variation in the monthly mean of the weather across the 10 ensemble members. We look at just the first and second ensemble member, as well as the reanalysis simulations. We see that the RASM simulations are following that of the forcing data, and this is as you would expect when applying nudging to the top half of the atmosphere. So now we're going to look at it in terms of monthly means averaged over the 10 years across the RASM domain, and we're also now combining the RASM alt simulations. Again, this is with swapping out the cumulus parameterizations. And we again see that in the upper levels, the RASM simulations are following that of the forcing data. And we're also able to see the biases in the DPLE data as well as in the resulting RASM simulation. The changes in model physics have little impact on the RASM state in the upper levels. When looking at the lower levels, again, we'll highlight surface temperature here. We see three clusters where we have the RASM standard configurations in one pattern of bias, warm bias, the RASM alt in another, and then the source data from the DPLE with a cold bias. And so the atmospheric state in the lower levels tends to cluster around the modeling system or the RASM configuration, yet we are still able to see the imprint of the weather from the different forcing data in the results. So now we're looking at surface radiative flux averaged across, on the left, the RASM domain, and then 3 different regions. And here we can again see the clustering of the results based on the RASM model, standard configuration, the RASM alternate configuration, as well as the DPLE source data. So the surface radiative fluxes are distinct for RASM, RASM alt, and CSM simulations, indicating that the model physics dominates these variables at the lowest levels. We can then take a look at the sea ice in the coupled modeling system and see that despite similarities in the surface atmospheric climatic state, the RASM DPLE simulations still evolve into different coupled sea ice states due to differences in the evolution of the weather. So here we're looking at the right, the sea ice extent for September 1995. At the end of the 10-year simulation, we can see this large range of sea ice state because of the different evolution of the weather, even though the climate state of the atmosphere is similar across the RASM simulations. So the conclusions are that the fully coupled RASM simulations were successfully forced with the DPLE output. Nudging above 500 hectopascals constrains the RASM's upper atmospheric state to be similar to the driving data and insensitive to changes in the model physics. Again, this is as you'd expect with the nudging. Meanwhile, in the lower atmosphere, RASM state becomes similar across the RASM simulations, regardless of the driving data, but varies with changes in model physics. Then throughout the depth of the atmosphere, regardless of the model physics, the RASM states mirrors the variability in the driving data. And we'll just leave with the acknowledgements. This is a contribution to the Highlight RASM project, which is funded by the Department of Science, the Office of Science and Department of Energy, and the simulations were done on Department of Defense, HVSM Computing Resources, and thank you for your attention.
So thanks, Mark. I see one question so far from Wei Wang, who's asking, have you considered spectral nudging?
The spectral nudging, when we implemented Wharf 371 into RASM, had some massive error bug that would crash it. And I worked with Dave to try to sort this out, and we were not able to sort that out. We did some studies previously with the RASM configuration and found the using grid nudging or spectral nudging was showing us similar results.
So currently you do nudging just above 500, that's grid nudging, right?
Correct.
Okay. I see Dave Stauffer has his hand raised. Let's go to him.
Yeah, could you put the conclusions back up, please?
Yep.
So again, I have to apologize. It went by so fast. DPLE source data. So what are you nudging? What exactly are you nudging above 500 millibars?
Temperature, U and V.
No, but from where?
The CSM decadal prediction large ensemble.
Okay, so does that mean, and again, so are you actually nudging RASM ensemble or just a single member?
A single member.
Okay, because again, you know, when you, okay, so from the ensemble, does that mean, how are you using the ensemble information in the nudging? Is it just a single field? Are you using, I guess I don't follow that. So when you nudge the U, V, and T from an ensemble, is that the ensemble mean?
We're running different ensemble members. We're nudging from a single member to create our own single member of the RASM simulation from the CSM DPLE member.
Okay, so are there more than one RASM simulation?
Yes. We have 10 RASM DPLE simulations corresponding to the 10 ensemble members in the CSM DPLE.
Okay, so you're not, I mean, if you nudge an ensemble to the same thing, then you would reduce the spread. So you're not reducing the spread because you're actually nudging to different ensemble members above 500 millibars.
Correct. Because we were trying to capture the different weather that is produced in the different ensemble members.
Just wonder why you chose 500 millibars.
That's roughly top half of the atmosphere.
Right, but does that mean you get a discontinuity, you know, at 500?
No, because we're using the ramping in the Wharf nudging. So we're nudging the top 20 out of the 40 vertical layers. We're nudging the top 20 layers, and it's being ramped up in layers 20, the first 10 of those layers.
But are you concerned that you're actually changing the vertical stability and the wind shears and the structures by this artificial nudging?
No, we're not concerned with that.
Maybe
and past studies that have focused on the application of nudging to these regional climate models have indicated no issues with that.
Yeah, I mean, it would be interesting just to try 850 instead of 500. So you say above 500. So is the 500 millibar level itself?
No, it's the top half. It's the top half of the model, the top 20 vertical layers, which is approximately 500 hectopascals.
So the level of non-divergence, which is near 500 millibars, you have minimal forcing from the nudging. Is that right?
Correct, because it's being ramped up to the 30th level where it pulls full in.
All right, thanks for the clarification.
Sure.
Okay, any other questions for Mark? And we can also open it to anyone who had a question on earlier talks as well as we come towards the end of this session.
And answering Way's question, yes, we do have plans to upgrade to the latest Wharf, as well as to leverage the tools of using a branch off, a fork and a branch off of GitHub, so we can do future upgrades more seamlessly than what is currently done. It's a pretty massive undertaking to do the upgrade due to the number of files that are modified, but it is on the to-do list. And yes, I agree, good.
Yeah. And we could open to questions on any of the talks. And Mark, who are the users for the RASM system? Is it basically is it a research project, or are there actually users who are getting these products?
It is a research project in that we're conducting science with it. There are using the CFS forecast. There is a product at Naval Postgraduate School that creates a sea ice forecast out 6 months using the different, our own creation of an ensemble using the different days of CFS forecast as the forcing conditions.
See, Dave Stoffer has his hand raised. Again.
Yeah, I have one more question. So where would you consider to be the main dynamic forcing, for your simulations? I mean, do you have, this is in the Arctic, I understand, but what do you think the most important level is for the dynamics? And when you nudge the temperature, are you affecting the geopotential height? So maybe I'll just let you respond. So where is the most important dynamic level for your runs? I mean, often, 500 and then jet level 200-300 for the mid latitudes, but you're up in the Arctic, right?
Yes.
So at what level is the weather most affected by? Do you have short waves? Do you have jet streaks? I mean, do you have anything like that going on, above you?
And so we're being guided in those levels with the nudge data. And so a lot of the dynamics is coming in the upper levels is coming from the CSM forcing data. And so part of the reason why we're also using the nudging is that then allows us to capture some of the higher level dynamics that are going on. I mean, what would we consider is pretty similar to what you would have with the mid-latitudes without getting into things such as the impacts of sudden stratospheric warming that has been shown to have implications for the Arctic.
Do you have to worry at all about vertical gravity wave propagation or anything that would be influenced by the vertical profiles? And the fact that, again, you're not nudging the same in all layers.
Yeah, we have not seen any issues with that, with the nudging.
Okay, thanks again.
Sure.
Mm-hmm. So I don't think I see any more questions, so we can hand over to Joe Klemp, who will close the workshop.
Thanks, Jimmy. I did have, since this is has been open for questions for all of the talks, I did have a follow-up question for Palavre in terms of whether he has given thought to trying to do some of these mid-latitude climate simulations with Mpass with variable resolution that would be higher in the mid-latitude zones.
That's a good idea, and we have thought about it, but I have no manpower to do this at this time.
Okay. Also, if anyone has any questions or comments related more generally to any aspects of the workshop, you could feel free to raise them at this time, since we are pretty much winding up here. So if there are any more general comments, feel free to speak up. Pretty quiet. Okay, one thing I wanted to do before we close is to make a couple of acknowledgements. To start with, I'd like to acknowledge Kelly Warner for her valuable assistance in the technical aspects of making all of this virtual workshop work smoothly in Zoom, and I think overall things went very well in all aspects of it. And I'd also like to give a shout out to Wei Wang for her significant efforts in leading all of the activities related to the organization and conduct of the workshop. So we, I think, want to thank both of them for their efforts. If anybody wants to unzoom themselves, or not.
Thank you, thank you. Thanks to everybody who contributed to the workshop. Without your presentation, there won't be a workshop. So thank you for doing that. Yeah.
Yes, I think we had really a pretty active group. I see our numbers have been dwindling down here as we're winding down, but it's been pretty active participation over the several days. So
especially to those who contributed from the other side of the world, it's not easy to to participate in meeting at your nighttime, but thank you. Yeah.
Right, we apologize for compromising your sleep during this period. As I mentioned in the opening remarks, we very much hope that next year we will be convening the workshop in person or perhaps a hybrid format. So we will be looking forward to seeing how we can work out the format for next year's workshop. So I guess if there aren't any other comments, I guess we'll draw this to a close and look forward to seeing many of you at next year's event. So thank you.
I would also like to thank Ryan for the work that he did to help us get this technology all in order. Ryan Johnson.
Yeah, yeah. The guy who stayed in the background. Thank you. Yes. Okay. Well.
Okay, very good.
See you next year. Bye-bye.
Thank you. Bye.
Thanks, Kathy. We are done.
Thank you. Yeah, I think it went pretty smoothly.
Yeah, no, I was so concerned about people not showing up, but everyone showed up. I'm very happy that, yes, okay, great. Okay, so we can take a little break now.
Get back to other work.
Okay.
Okay.